Yes, sure. Share. Uh, oh, I think I have to tell my computer that Zoom is okay to share. Uh, maybe it's going to work. Okay, can you see my screen now, or can you
Yes.
see the presentation?
We see the presentation full screen now. Yes.
Okay, great. So this is just a quick overview of what SAR missions have been available in the past and today. Um, it's been a long time since the first SAR missions, but these are the key satellites that yeah. Are you seeing these things in front of the? I'm going to get this over to the side.
We can see your mouse pointer and we can see your slide. Yeah.
Okay. Let me go back. Why is it not going back?
We're definitely going forwards.
There it is. So the the first satellites that people used extensively for interferometry are the ERS-1 and ERS-2 satellites. ERS-1 was launched in 1992, and ERS-2 was launched in 1995. And they operated almost all the time in a 35-day repeat. ERS-1 had some different phases at the beginning of its operation, where they had 1 day, 3 day, and 183-day repeats while they were testing out some different mapping modes. And this is an a C-band 6 centimeter wavelength. Another early satellite system was the Canadian RadarSat-1 satellite, which was launched in 1995. RadarSat-1 was partially a cooperation between the Canadian Space Agency and NASA. NASA provided the rocket for RadarSat-1 launch, and the CSA built the satellite and operated it. But that gave NASA the right to have all the data that was downlinked at the Alaska Satellite Facility be available through ASF, and also to make they actually turned the satellite around for a few months and did a full map of Antarctica during the RadarSat Antarctica mapping mission. They turned the satellite around, so instead of looking right, it looked left. And so RadarSat-1 had a 24-day repeat, and I think that the Canadian Space Agency is now making that data available to everybody. But for a long time, it was restricted, except for the part that was at ASF. Then the next main follow-on from the European Space Agency was the satellite called ENVISAT. ENVISAT was a huge satellite. It had not only the SAR, it had optical sensors, several different optical sensors. It was launched in 2003 and continued operations until 2010. In September 2010, they actually changed the orbit. It had been in a 35-day repeat. They lowered the orbit and let it drift to some extent because it was getting low on fuel, and it was then in a 30-day repeat orbit. And again, that's a C-band satellite. It was in basically the same orbit as ERS-2 And it was only an hour apart. So there are some cases where people have done interferometry, but the radar frequency was different. So in fact, you had to use pairs that had very long baselines so that the baseline effect on the radar frequency canceled out the difference in the frequency between NBSAT and ERS. So there are some interesting sort of experimental results with that. Then the Japanese Space Agency launched the ALOS satellite. Because they later launched other ALOS satellites, the people started calling this ALOS-1, but in fact, it was originally called just ALOS. That was launched in January 2006, operated until April 2011. It had a 46-day repeat cycle, which is quite long, but it was an L-band satellite. So the coherence stayed pretty good over 46 days in many places. The disadvantage of the way they operated the ALOS satellite was that they did not adjust the orbit. So the orbit gradually got longer and longer between 2006 and 2008. Then they did a huge correction to the orbit and moved it back to where it was at the beginning. But that meant that there was, you can only form pairs over short time intervals and 2-year time intervals with the ALOS satellite due to the way they operated the satellite. Then TerraSAR X was launched by the German Space Agency, DLR, in 2007, and then followed up by a second satellite that was identical called Tandem X. Those two satellites are still flying, and they fly very close to each other in the same orbit, but a few hundred meters apart. And that's the Tandem X and TerraSAR X were operated together in bistatic radar to make where the signal was transmitted by one and received by both to make a global map that's now the basis of the Copernicus DEM. And that's they had 11-day repeat, and it's an X-band satellite, as you can guess from the X in the name, with 3-centimeter wavelength. And then the same year, the Italian Space Agency launched their first Cosmos SkyMed satellite in 2007, and they launched a total of 4 of those Cosmos SkyMed satellites. Each satellite has a 16-day repeat, but through the phasing between them, there's pairs with 1 day, 4 day, 7 and 8 day separations, and that's also an X-band satellite constellation. The Canadian Space Agency launched RadarSat-2 in December 2007. Due to the nature of the agreement between Canadian Space Agency and NASA, the access to the RadarSat-1 data was terminated after RadarSat-2 was launched. RadarSat-2 has roughly the same orbit, 24-day repeat, and it's C-band. But until recently, when they started opening up the RadarSat-2 data, it was primarily used for commercial operations and was available to only people at Canadian institutions. So this is just a quick overview of how these satellites can be processed with the ICE2 software. I don't think the ICE3 supports any of these satellites at the present time, although I understand Haresh has been looking at trying to support some of these older satellites. With ERS-1 and ERS-2, you can process either the raw data or SLCs. With ICE2, RadarSat-1, you can process with if you get the raw data. They didn't provide SLC products for that. You can't. They also had a ScanSAR mode, and that's not possible to process, especially because they didn't. Well, they didn't have burst synchronization.
Also, the orbits are dreadful, right?
And the
orbits.
orbits were dreadful. They let the satellite drift a lot, and not only did they let it drift, but they um, didn't have good quality measurements of the orbit. So that even after the data has been acquired, you have to estimate what the error is in their orbit determination. But it did provide data over some areas that weren't available from ERS-1 and ERS-2. And one of the key things about ERS-1 and ERS-2 is it did not have any kind of recorder on board, so it was only able to acquire data where it was within sight of a ground receiving station. So there's good coverage over Europe and North America, but some other parts of the world, they had put up receiving stations temporarily while they ran the 1 day repeat between ERS-1 and ERS-2 in 1995 and 1996. But those were temporary receiving stations that were removed later. The ALO satellite, no, ENVISAT, you can process the raw data, the strip map data. ScanSAR is not really supported by ISCE2, but people have processed the ENVISAT ScanSAR data after they worked on synchronizing the bursts. The ALO satellite had 3 different modes with different polarizations or range bandwidths, and you can process both the raw data and SLCs. TerraSAR-X, they only make available the SLCs. You can process strip map data and their spotlight mode, but not the ScanSAR mode. And similarly for Cosmos SkyMed, you can process the SLCs from strip map and raw, and in some cases people got raw data for the strip map that's also processable with ICE2, but not the ScanSAR data. RadarSat-2, it is possible to process the strip map data, SLCs, for the few scenes that I was allowed to get, but we due to the low availability, it's not been tested much. These are the very old, some of the other satellites that not very much used for interferometry. The United States, NASA actually launched the first civilian synthetic aperture radar satellite in 1978, as Haresh mentioned. It operated for 110 days. It had a L-band radar wavelength, and it had 2 different repeat cycles during those days, a 17-day repeat and a 3-day repeat. Some of the 3-day repeat data has been used to do interferometry. In fact, the first interferograms, the first differential interferograms were made from CSAT data over the Imperial Valley. Japan Aerospace Exploration Agency did have an earlier satellite called JRS-1. I think Gareth tried to process some of this data. That also had very bad orbit control and orbit accuracy, and
yeah, nice residual ramp once I managed to actually process it, but it was possible.
But that's the only L-band satellite that operated in the 90s until they launched the ALOS. But another important thing was the shuttle imaging radar mission operated by NASA and built by JPL, called the Shuttle Imaging Radar Mission C. There was a shuttle imaging radar A and B, but SIR-C was the first mission that had a large amount of data. acquired. It operated, did two flights in 1994, each of 10 days. On the second flight, they did some one-day repeats. And there was also one day of the second flight that they made it repeat the same orbit as the earlier flight, so we have a 6-month repeat. And the shuttle imaging radar actually had X, C, and L band. So this was a multi-wavelength radar, but since it was on the space shuttle, it was only operated for 10 days. But it does give some interesting comparisons where we can see the L band and C band and X band coherence from exactly the same time intervals. Then there's the new spacecraft that are in use today. Of course, we've been talking a lot about Copernicus Sentinel-1. Sentinel-1A was launched in April 2014, but it didn't reach the final orbit until October 2014. And then it had a long ramp up. So there's really not much data before March of 2015. But it operated all the way through to June of 2026. So it was in space for 12 years. And what that is. Sentinel-1B was launched in April 2016. It stopped working in December 2021. So for a while, they were back to having only one Sentinel-1 satellite. While A and B were operating, there was a 6-day repeat. Then we had to wait until December 2024, or 3 years, before they launched Sentinel-1C. That then got the constellation back to 2 satellites with A and C, getting the 6-day repeat again. And then Sentinel-1D was launched in November 2025. And then in June of this year, June 2026, they had Sentinel-1D 1 day apart from Sentinel-1A, and they got some 1-day repeats that way. But at the end of the month, they moved Sentinel-1C to be 6 days apart from Sentinel-1D, and they decommissioned A. So they're back to 2 Sentinel-1 satellites in a 6-day repeat between the 2 of them. And they're both new satellites and expected to last at least 7 years each. So until 2030, early 2030s. Japanese Space Agency launched ALOS 2 satellite in May 2014 for strip map interferometry. They started collecting data pretty much right away. They didn't get the burst synchronization for their ScanSAR working until February 2015, but there's a very large amount of ALOS 2 ScanSAR data that's now at the Alaska Satellite Facility and available for free download. And that's an L-band satellite with a 14-day repeat. So pretty similar to NISAR, but due to the limitations of the satellite, the amount of data the frequency of acquisitions is much less. With the ScanSAR, it's 350 kilometers wide, so it's wider than Sentinel-1 and NISAR. And there's full overlap between the tracks. But the strip map data, with its 70-kilometer width, they actually need to use 3 different strip map beams to cover the distance between the tracks. So that greatly reduced the strip map coverage. And JAXA is not making the strip map data available for free, only the ScanSAR data.
And the ScanSAR files are gigantic, right? The SLCs.
Yeah, the SLC files are 60 gigabytes, which is gigantic, but the NISAR GSLCs can be up to 20 gigabytes, so it's approaching the same level of disk space. Indian Space Research Organization launched a satellite called RISAT-1, which was a C-band satellite that operated for 4 years. And then we have NISAR. Haresh gave a great introduction to NISAR. I'm not going to go into that in any detail here with the 12-day repeat and the L and S band radar frequencies. So Sentinel-1 satellite strip map data can be processed by ISCE2 from the SLCs. There are some places where they still acquire strip map data because they're of certain like volcanic islands. I think they cover over Piton de la Fournaise and a few other places. But most of the data is collected in TOPS mode. TOPS mode, as Yunjun explained, is a type of ScanSAR with three different separate beams, but it has this scanning method, which makes it extra complicated to process. But it's supported by ICE2 and by ICE3. The ALOS-2 satellite is supported by ICE2, the ALOS app, ALOS-2 app, and ALOS stack processors for the strip map SLCs, ScanSAR SLCs focused with the full aperture method, and also the spotlight mode. And there has been some testing with ICE3 for processing the SLCs from the ALOS-2 strip map mode. But I don't think that's part of the released version of ICE3. And then RISAT-1 can also be processed with ICE2. There are other new satellites by several. Argentina launched two satellites called SAOCOM-1A and 1B in 2018 and 2020. They're both still in operation. They're both L-band satellites with a 16-day repeat that's basically a similar orbit to the Cosmos SkyMed constellation. Between the two of them, get an 8-day time interval, but the satellites have a very low capacity for acquiring data. They have it has a TOPS mode, but that's not burst synchronized, so it can't be used for interferometry. The SAOCOM strip map data can be used for interferometry. Japanese Space Agency launched ALOS-4 satellite in June 2024. It's in the same orbit as ALOS-2. It's similar, and it's exactly the same radar wavelength and orbit. So there are ALOS-2, ALOS-4 interferograms possible from the strip map modes. ALOS-4 has a different ScanSAR mode, so it's not compatible with the ALOS-2 ScanSAR. And ALOS-4 is only available to people that have grants, data grants from JAXA, so it's limited availability at this time. Maybe they're going to change. The Cosmos SkyMed Italian Space Agency launched a second generation or next generation Cosmos SkyMed NG in 2018, between 2019 and I think I haven't updated. I think they've launched all four of them by now, and it's an X-band satellite. But again, it's largely available only to commercial customers and people that have data grants. The Canadian Space Agency launched another RadarSat constellation, which of 3 satellites together in June 2019. So, but with those 3 satellites, they get a 4-day repeat. But again, they limit access to the data. I think they have been making some of the constellation RadarSat constellation mode data available. Other additional satellites, South Korea had a SAR satellite called COMSAT 5. There was a X-band satellite. The Spanish Space Agency launched a satellite called PAS, which was basically a clone of TerraSAR X in 2018. So it's in the same orbit as TerraSAR X, but it's 4 days apart or 7 days apart. And they have had some programs where they make the PAS and TerraSAR X data available. And they're also available through the NASA Commercial Satellite Data Acquisition System for people in the US. The Capella has launched a number of satellites. I don't know what the up-to-date number is. If Scott's on, he could update us on that. Scott has shown some interferograms that had a 3-day repeat in a few places. So that has it's an X-band satellite. So their strip map data can be used for interferometry. ISCE has about 40 operational satellites in their constellation. It's another constellation of X-band satellites. Some of their satellites have as little as 1-day separation and are used for interferometry. Another company called Umbra in the US has a plan for 24 satellites. I think they've launched around 12. But they don't have InSAR capabilities set up. They're quite small satellites with a limited maneuvering capability. And then there's been a number of other satellites launched by China and Japan and especially some private companies. ISCE is originally a Finnish company, but they also have a US subsidiary that they use it's based in Irvine, California. And then there's NISAR. We all heard about that from Harash. It was launched just over a year ago, and they started full science operations in December 2025. So these are just some of the software links that I included in this slide set. We mostly talked about earlier. There's the websites at ASF that have the most information. And we've also taught the NISAR RSET course just last month, and the recordings from that are available along with the slides and I used a Jupyter notebook to no, that one didn't have a Jupyter notebook. I just used a demonstration of QGIS for looking at NISAR GONW files. So that's a quick overview, and if there's any questions, I can answer them.
Thank you, Eric. Questions? There's one in the Q&A. If you want to have a look, Eric.
Oh yeah. Is there a signal interference between the satellites? That's a good question. I don't know of cases that's happened, but I imagine that it's bound to happen, especially with all these X-band satellites. The X-band available bandwidth is very large, so they may not be using the same frequencies exactly. Umbra has a mode where they actually have a range bandwidth of 1,200 megahertz. So they get down to like 30 centimeter resolution. It's kind of strange because the Umbra satellite's range bandwidth is the same as the center frequency of the L band for NISAR. So the frequency of the X band is 9 gigahertz. So they're using a big part of that 9 gigahertz range bandwidth. They primarily operate Umbra in spotlight mode, which makes it much more difficult to get interferometry because you have to make sure that not only the orbit's in exactly the same place, but you have to be pointing at exactly the same point for the spotlight mode.
I imagine
I have done
co-registration.
I have done interferometry with TerraSAR-X spotlight mode data, and it works quite well because they make sure that the center point of the spotlight mode is lined up. Oh yes, there's the biomass that the European Space Agency launched the biomass satellite last year, which is P-band, and it does some interferometry. It's, as you can guess from the name, it's designed for measuring biomass, but they have trying to use interferometry to do some tomography to measure the volume scattering within the forest and get the tree heights. It's P-band, so the radar wavelength is around 70 centimeters, much longer than L-band, and that means that it's much more affected by the ionosphere than NISAR and other L-band satellites. And the big problem with P-band is that the radio frequency allocations are much more restricted. They're not allowed to operate biomass satellite over the United States or over North America or Europe. They only operate it over Africa, South America, and maybe parts of Asia. The United States military uses P-band radars to watch for incoming missiles. So they wouldn't allow them to operate the biomass over the United States. Even over South America, they're only allowed to use a range bandwidth of 6 megahertz. So the spatial resolution is highly constrained by the available range bandwidth. And they're fighting with the ionosphere. I understand that they had a lot of results at the ISCE fringe meeting and EU-SAR last month.
Any more questions for Eric? It would appear not. Thanks, Eric. That was great. And I'm going to move on to the next item on the agenda, which is Rowena talking about decomposing line of sight measurements into their component parts. Go for it.
Hi, and I'd actually like to share something else just because there was a lot of questions about soil moisture. So this is just to wake you all up. Let me just share my whole desktop. That's the easiest. Things out here. Okay, so a lot of you may be aware there's been a pretty extreme drought in much of Europe and particularly in southern England. Lots of pictures in the news showing Stonehenge all dried out. And it turns out NISAR data is able to capture the signal pretty well. And I want to just use this as a quick plug for a worldview. If any of you haven't played with this yet, it's a really nice way to look at some of the data that's out there, including NISAR now, which is a fairly new addition. So if you want to add NISAR, you just click on Add Layers, and you write NISAR up here, and you'll see there's a false color radar backscatter version right here at the top. There's also a 12-day one. I'm going to suggest you start with this one, and then we go back, click here. And now you can see this is basically one of those composites that has one polarization in one band, another in a different band, and then kind of their difference in a third band. And if we zoom in to the area near Stonehenge, which is down here, I'm just going to zoom up here. So this is data from, sorry, one of the NISAR tracks on June 17th. So it's right at the beginning of the public data that that everyone now has available to them. And sorry if that wasn't working. If you want to just kind of scroll through NISAR images for the same exact track, you can click on custom down here at the bottom. And there's, I've already set this, but you basically pick an interval. I've made it 12 days. And now you can basically just step through the data in 12-day intervals up to the present day. This is the most recent image we have for this track. So you can see it's much brighter at the beginning. And with soil moisture, the surface tends to be brighter if it's wetter. And so what you're seeing as all of these fields are darkening, you're seeing that drought basically come into full swing. These little green lines, you see a lot of these are hedges or forested areas, some of the cities. Those areas tend to be brighter, but these darker fields are what we're able to really see with NISAR. So if you're interested in the soil moisture product, I'll be in the office hours tonight and in the morning, and I can answer any other questions about them then.
Also, if you say you're going to be as quick through the notebook as you previewed to us, then you have more time to talk about it in this session too.
Yeah, so if you're willing to let me have the whole time, I can answer.
I am willing.
All right, so let me just close that. So what I'm supposed to do today is talk about this wonderful notebook that Gareth put together a while back now. But it really addresses a lot of the questions I've seen on the Slack and in the chat or the Q&A about how do we actually combine InSAR data that has different lines of sights if we want to, say, understand something about what the surface is doing or infer the characteristics of, say, a subsurface model, like a fault plane slipping or something along those lines. And in the homework associated with this, one thing I just want everyone to be aware of is this year, for the first time, I changed it so that instead of just uploading your notebook, there's a quiz you're going to take. And I did my very best to make the answers be correct. But there is a chance, as with any of these things the first time, that something is going to go wrong on the student side. So again, I'm going to be watching the Slack a lot more carefully today and in the office hours to hopefully debug any issues with that. But the hope is then you'll get your response quickly to the questions on here. And they kind of are kind of yes or no, multiple choice type questions. So they should be they're ones that are pretty easy to grade in that respect. Okay, so just another thing is, since people were confused about this last year, I'm not actually on OpenSAR Lab right now because I didn't want to fight with you all for resources. This is just running off my desktop. That's why my environment looks a little bit different. But this first notebook only uses NumPy, so it doesn't really, any of you could run it on your laptops probably. So the data that's being used in this notebook is from Berkeley, California. And this is actually the result of a fairly large set of InSAR data that has been processed and displayed. Let me just show you the image. This displayed, as you can see here, each of these dots is a relatively stable scatterer that kind of retained its scattering characteristics over the time span of this particular time series. And this first one that you're going to see as you scroll down is from a combination of the ERS-1 and ERS-2 satellites that Eric just helpfully described for everyone. And the data spans really, really old 1992 to 2000 data. And what you're seeing here is basically the average velocity in the satellite line of sight for this particular track over this time period. And what's kind of in color here, again, is the line of sight velocity. And these little kind of pink polygons you can see here are the outlines of known landslides. And even just looking at the color here, you can see that they are moving at different rates to their surroundings, much of which are, building tops, roofs, things like that. If you kind of step back and squint, you probably should also be able to see that this side over here, where my pointer is on the upper right, is a lighter blue color than kind of a light bluish, almost purpley color compared with the turquoise in the lower left. And this is because you're actually seeing a creeping fault going through here. It's the one that cuts through the stadium on the Berkeley campus. Excuse me. And so one of the things you're going to see later on is each of these labels here, 1, 2, 3, 4, 5, has a number in it, which is the average line of sight velocity within each of these polygons. So they're all moving at between 2 to 3 up to 12 millimeters per year. Okay? So the other thing to note in these figures is that you've been given the geometry of this arrow that tells you what which direction the satellite's moving in. So this T direction here is the traveling direction of the satellite. In this case, we're looking at a descending track that's moving towards the south. And so this 191 is the degrees, the azimuth of this orbit in degrees from north, right? So you go all the way around to 180 and then past that a little bit to 191. The theta value here is the look angle. So this is 23 degrees. We're only using a single value for this entire area in this problem, but you'll see on the other notebook that you can be more complex about that if you want. All right, so if you move down, sorry, I didn't have the color bar on there. Hopefully you can all follow along. This is now data from the RadarSat satellite that now spans a slightly different time interval, 1998 to 2006. And again, we're seeing the average line of sight velocity. So this is basically fitting a line to the time series. And just before we go on, I want to make a point that when anyone does this sort of thing, one of the assumptions you're having to make is that the actual ground motion that you're seeing in these plots is basically representing the same source, right? So here you're looking at two separate time intervals. And as we go forward in this exercise, we're assuming that the rate is the same over that entire time period. This is clearly not true. It's just an assumption one has to make to kind of move forward in this, but it is something you should keep in the back of your head whenever you're looking at a problem like this. So in this case, again, we're looking at the average rate, this derived from many, many different SAR images. You could also look at an interferogram spanning a single earthquake, say from two different tracks. If you do that, then you have to think about, does one of the interferograms span more interseismic motion or more post-seismic motion than the other, so that really you're not looking at the same thing? If you are pretty confident that you're only seeing the one signal, or at least they're both seeing the same, most of the same signal, then you can move forward with this approach as we're doing here. So here now, the satellite is now moving towards the north. This is an ascending satellite. In this case, the azimuth is 348. So we've gone from north all the way around, almost back to north. And the look angle is 34 degrees. So you're going to need those numbers to finish up this notebook. Okay, so there's a bunch of stuff in here that I do recommend reading. In the homework, you're going to be asked, does this make sense? For instance, in this case, this side of the image is uphill and these landslides are moving downhill, presumably. So you're thinking of, if the satellite's looking in this direction and you're seeing negative line of sight, that means the line of sight is getting shorter. Does that make sense? So in this case, they're moving down, which would make the line of sight, presumably they're moving downhill. So part of that motion is down. That would move it away from the satellite. That would be a positive line of sight. But they're also moving towards the west, which would make a shortening of line of sight, right? So kind of think in your head about how the true ground motion would get recorded from this particular look direction. So again, we have the average of the value in all these little dots within each of these polygons you're going to see later on in the script. You won't have to write that down like you do with these values, but for the azimuth and look direction. But excuse me, it's still good to just see if they make sense to you and if they're the right order of magnitude. Okay, so then if you I strongly, again, encourage you to go through these figures to make sure that you understand what's going on. What's shown here is basically the first image is what it looks like if you're traveling in the same direction as the radar. So the radar is moving in or out of the page here, and it's looking in the direction of this orange vector here, right? So this angle here is the look angle we've talked about previously. And you can see from this geometry that if this is the angle theta here, be same here, then the horizontal component would be the sine of that angle, and the vertical component is going to be the cosine of that angle. All right, that's what's kind of written down here. And this vertical component is basically going to be that no matter which direction, north or south, the satellite's moving. The vertical portion is going to depend on the look angle, and that's it. So you're going to see that on its own. This horizontal component, whether that's north or east, depends on which direction the satellite's moving, right? So the slightly more complicated geometry in the next figure, now we're looking down on the ground. The satellite is moving in the direction of the V vector here, the purple vector. And again, it's looking in the direction of the orange vector. And so if you have this horizontal component you just calculated based on the look angle, then how much of that is north versus east is just this sine term that has the azimuth in it, right? So this is what you're going to end up seeing below when we try to break apart what should a unit of north deformation look like in the line of sight given a certain look angle and azimuth. All right, so if you have, what you end up with is, make this a little bigger, is this vector here where it's basically the component in the x direction, the y direction, and the z direction, and how it relates to the look angle and the azimuth direction of the satellite, right? So it's fairly simple equations, and this is what we're going to use below. So as you go through the homework set, you're going to come to this cell where all of these are going to be blank. So you will need to fill these in based on the numbers above. And if we do that, I'm just going to run all because I forgot to run the earlier one. If we put those in and we run it, it calculates these vectors just using the math we had before. So here, for instance, is the look vector for the ascending direction. So this is the x component, the y component, and the z component. And again, the way to think about this is what does one unit of positive motion do to the line of sight vector for this ascending track? So this last value here, which is negative and close to 1, is what would happen to 1 unit of upwards motion, right? So if the ground moves up by 1 meter, then the line of sight will shorten by 0.8 meters, right? It's going to be negative because you're getting closer, and it's going to be a little smaller than the full 1 meter because some of that is in the horizontal, right? So you're seeing about half of a meter, excuse me, if you had 1 meter in the east direction and a very small component in the north direction. Right? So this is for the ascending satellite. And you're going to be asked in the homework to go back and look at the image and think about whether that makes sense. If we do the same thing for the descending, we get a different line of sight vector. The vertical component is still negative, right? And because we're still moving up, makes the line of sight shorter. But if you compare the horizontal components, here they are here. So here's the descending one, which was the first image we looked at, and here's the ascending one. Note that the sign of the east-west component is different, right? And this makes sense. When you've got a right-looking satellite, it's moving to the south. It's looking in basically the opposite direction than when the satellite is moving to the north, right? So you have different effects on the line of sight for the same amount of displacement in an east direction. Note that the northern direction is the same sign. If you look at how those vectors are pointing, it should make sense. And that the vertical component is much smaller than the other two, but it's not 0, right? If there is a unit of northward motion in your true ground displacement, it is going to actually affect the InSAR too. All right, so you'll have a few questions again that you'll answer in the quizzes. So now what you have basically is you have 2 ways of converting 3-dimensional deformation into the line of sight. And we have two different line of sight vectors. And so for any sort of inversion, you need to have more equations than you have unknowns. We have two equations because we have two different lines of sights, but we have three unknowns, right? We've got X, Y, and Z displacements we'd like to infer. And so we can't do that. It would be kind of like trying to fit a line to a single point, right? There's the limit to what you can do without making some more assumptions. And so what we're going to walk through is what does it look like if you assume the motion is all in the east-west or vertical direction? There are other assumptions you can make, but we're going to just do this one here. And so we're going to basically define a vector, which is basically the horizontal and the vertical velocities. Where here we're going to basically be thinking that the horizontal is the east-west motion. And we've got a vector. So this is what we want to know. We want to know what the east-west motion and the up-down motion is. And we've got our two vectors of range change. These are going to be those average values within each of the landslides. And so if we know that true deformation, and we have this matrix P that I'm going to show you in a second, that's basically how much does these line of sight vectors, how does it convert the true deformation to the line of sight? Then we can predict what the range change should be. What should the line of sight deformation we observe look like? This is what we call the forward problem. This is basically taking a model where we think we know it and we're predicting our observations. And so for any of you who've had inverse methods in the past, ignore the red. These next few steps are basically reversing that equation in a bit or inverting it in a way that this is called the least squares solution to that problem. And it allows you to basically infer the model itself given your data, right? So given a set of line of sight values and your knowledge of what the line of sight vectors are, what is this matrix that relates these two to each other, what would the best fit north and east displacement be? And so this next bit is basically done for you. You basically take these P underscore ASC and P underscore DSC are from above, where we had those components of the look vector. You see that we're using the 0th and 2nd term, which is the east-west and vertical one. And if you remember, these two had different signs, and the two vertical ones had the same sign. That is basically the main way that makes it much easier to kind of decompose these two different line of sights. So when we put that together, we get a matrix that's just a 2x2 matrix. So here are the horizontal components, different sign, and the two vertical components. Here below are all of those average velocities. So this is our data vector. So here's the ascending ones for the 5 different landslides, and then the descending ones for the same landslides, right? So same polygons is just what was in those pink values up above. This PTP inverse is just something that's used a bunch. It's the equation we saw up above here, that if you're interested in this, any course on inverse methods, or even it's the same math you use when you fit a line to a set of data. You can find more info about that in lots of places. And so when you solve for it, you end up just taking this term here. Here we are looping over each of the different landslides. You're basically taking the data, the range change for just that, the first or the second or the third landslide, and then solving it for the east and north components, just using the equation we just showed you, and then printing them out. So when you see this, you should end up with something kind of like what's shown here, where there's the 5 landslides, and in each case there's a negative east velocity, which means it's moving towards the west. So again, you want to think about whether that makes sense. And then a vertical velocity that's negative, which means it's going up, except for one of the sites here. So you can think about that on your own. And then there's a whole bunch of more citations below if you're interested in. Okay, so that's the problem you're going to work through, where what they're doing there again is you're taking one line of sight vector for the whole region, and you're looping over these 7 average values within a set of data that came from many, many, many images. The other notebook, which doesn't have a question and the homework associated with it, I probably should add one next time. But it's a much more realistic problem for what I've seen people asking about today, which is, let me just run this again to make sure it's gone. Here, instead of just using one line of sight and and averaging over a number of pixels ourselves, we're going to basically look at a whole image and do the same math over that whole image. And so again, most of the stuff here is the same, except you do use MintPy, so you need to have that working. You all should. And the data set that we're looking at here, this is just loading it. All of this should be in the folder associated with this problem set. And so let me just go down to the images. Most of what's being done here is just reading these larger data sets and cropping them to a certain region. And here is the two images that you're going to come out with. So here's the descending line of sight velocity. In this case, it's on a big grid. This is actually in Eastern California, associated with a geothermal power generation area. And so the descending, you're seeing quite a bit of negative values right here and kind of mostly yellow positive values around it. And then here for the ascending, you again see a bunch of negative values in the middle. So the first thing you should remember from the previous exercises is when both ascending and descending have the same sign, that's pretty consistent with the motion being primarily in the vertical direction. Okay, so we should go in to this thinking that a lot of what we're going to invert for is going to give us a big signal that's mostly vertical in the middle. And so the what's done here, this is stuff that you've probably seen already with MintPy, is that they loop over all of these different images. Let me just show you the end because I want to make sure we have time. And you end up with...
We have lots of time. You can go through it more slowly if you want.
Okay, sorry. I want to talk about soil moisture. This is the same math as the other one. And so there's basically now an image of east-west velocity and vertical velocity across the entire area. And so it's just what we would kind of expect, right? In the middle, you're seeing one big lobe of these negative values. And in the horizontal, you're seeing motion basically radially away from that central source, right? And so this is what we would expect for basically a pressure, almost like a Mogi source in this central area. Okay. Sorry. So hopefully you'll all have time to look at that a little bit. The other thing it also plots some of these outputs to files, which is nice if you want to learn how to do that with GDAL. The other difference between this problem and the previous one is that you're actually reading in a grid of information about the satellite look direction and stuff. So at every single pixel here, the line of sight vector is slightly different, right? So that's, again, more realistic for what you might be doing in a big, large area of study. All right, maybe I'll stop now to see if people have questions. I see that there's one that Gareth's already answering.
Yeah, the question is, can you do this with time series? And my answer I am writing is that yes, but time series often have lots of noise in them comparatively compared to velocities, which is like the average trend over a long period of time. So you have to somehow smooth or account for the noise in the time series. And also, of course, the other issue would be that your different InSAR data sets might be acquired on different dates. And so you also have to harmonize that somehow. So I have experimented with taking moving averages of the time series and things like that. And it's still a bit dicey. But this is the sort of thing that people are starting to do more and more of and develop methods for. It's kind of at the frontier of what we're trying to do with time series, I would say. And now we have NISAR with the capability of with a left-looking sensor compared to the right-looking ones, we might actually be able to do full 3D decomposition of time series.
Yes. Yeah. I think very briefly addressed this at the beginning, and I think this is worth going through some more. Every interferogram is a time series, kind of. That's how I like to think about it, right? It's always it's not a single event. It's a summation of however much deformation occurred between those two dates. And so, as Gareth said, what you're doing by having more dates go into whatever rate you're looking at is you're reducing the amount of noise, but you're also, trying to nail down what time interval you're looking at. And so let's say you had a 1 year time series that you'd fit a line to in your ascending track, and say 1.5 years for the descending track. Maybe you're looking at an earthquake or something like that, right? Now you have to worry about the fact that you might have a hydrologic cycle where things are kind of going up and down once or twice a year, and one of your time series samples that differently than the other, right? So that assumption you made about I'm seeing the same thing except for white noise is likely incorrect. And okay, so you got that one. So I'm just looking at the questions.
There was a question about interpreting the east, north, and vertical velocities, but I think the first thing to do would be what do you actually see in them?
Right.
I mean, you can tell me what it's doing. You can look at what way is it going, up or down, which side of the reservoir is moving in which direction, and then we can talk about it. Don't make us just tell you the answer. Come on, let's do a bit of thinking.
You are all typing rapidly to answer the questions, so I won't go after those. The other thing I wanted to bring up was that this is one approach. If you look at this problem here, we kind of by construction made our P matrix only include the east, west, and north and vertical motion. We ignored whatever happens in the north-south direction. But if you have a unit of motion in the north-south direction, it is contributing to your data, right? And so if you were to add another column to that matrix P and try to run this, which I think is something a lot of people get tempted to do, you're basically trying to invert a matrix that does not have enough information. It will still work. You'll get an answer. And what's happening if you do that, if you actually put in, instead of just doing ascending and the 0th and 2nd columns, if you put that first column in there and then go down a few cells and try to run it, it's actually going to give you an answer. The reason that's bad is that Python, or NumPy in this case, is assuming you don't really want to invert a singular matrix. It tries to help you. And the way it does that is by turning this inversion that we see here into a damped least squares inversion, right? So it'll put a constraint on the solution and it'll give you something that is an answer, but it's not the right one, right? So something I like about earlier coding is if you went and tried to invert that matrix, it would just fail. It would complain that this was a singular matrix. And one of the kind of pitfalls of more modern computing languages is they'll try to help you along, and sometimes the choices they're making aren't what you want to make, right? So it's just one thing to say about that. There's other stuff you can do, though. Another approach people use to invert for east, west, north, south, and vertical is to bring other information about what the real Earth really does, right? And so, for instance, we know that it's unlikely that if you push down on the Earth, say, or pull up on it, to whatever extent it behaves like an elastic medium, it should move in the horizontal direction as well, right? So if you push down on it, some of it should be moving away, right? So you can actually add that as a constraint. Depending on your problem, this may or may not make sense. And so that's something you could do to invert for, say, all 3 components, even if you only had, one line of sight. You'd be bringing a lot of assumptions about how the Earth behaves, but sometimes those can be valid. And the other thing is you don't necessarily have to invert for east, west, and vertical motion. One of the questions earlier was talking about this. And let's say you have a fault plane, like the ridge crest earthquake. You have some known fault orientation and depth that you have really good reason to believe is the right fault. You don't have to convert to east, west, and vertical before you do an inversion, right? You can basically take that same matrix of what the line of sight looks like and basically project your predicted deformation into the line of sight of both of your, or however many look directions you have, right? So you basically work in the original coordinate system of each satellite, and you do that all at the same time, right? So let me answer this question here. Brian, you had a question?
Yes. In the earlier lectures, you guys had mentioned that the pointing vector for the line of sight is the dot product with the displacement vector. And so the north-south direction, if it was 90 degrees, then that third component, wouldn't it go to 0? I don't fully understand
It's
why
not,
we have
okay.
three components. Wouldn't that 90-degree component cancel out?
If your satellite was moving pure north-south, you wouldn't see it. So the problem is it is slightly off of north, right? So there is if this is that horizontal vector, there is a slight component in the north direction as well.
Oh, I see. Thank you.
It's much smaller. That's why we often ignore it. Why is it? Okay, so a question about why phi is measured this way here. I want to really caution you that pretty much every single satellite provides this in different coordinates. Sometimes there's one of them, you get it in the angle from east. So be very careful when you start looking at a new satellite to make sure to just look at what these choices were and what azimuth actually means, right? Because it does vary between satellites.
But trigonometry is clever. It accounts for all these things. So as long as you draw it, I always have to draw it. That's why this figure is in the notebook.
This is why all of us who were in grad school in the early aughts, our brains are still sharp because we have to keep doing this. It was what we did while we waited weeks for the images to arrive on CD or tape.
And for NISAR, the angle that they give is the angle of the look vector from north, not the track angle from north.
And I haven't worked so much with this, some of these other tools like MintPy because I tend to just write my own. But I think a lot of them have actually done a lot of this math for you. So you don't have to worry so much about what the exact sign convention is. But it's good to be aware of and try to make sure that what you get out at the end of the day makes sense.
Right, this will invert for 3 component directions locally, which means the inverted answer, positive is up, and positive east is east, all those things. Because the pointing vector is negative and pointing downwards in this particular case, because the interferograms are in range change. If the interferograms are in ground displacement, then you have to change your pointing vectors to account for that. But when you do the inversion, you should still solve for local vertical, local east, local north, if you're still from north. And people are asking, how do you do this to solve for north if you have something that measures or is sensitive to north? Well, you just don't throw it out. You would actually invert it. I really recommend the references at the bottom of this page. There's the paper by Tim Wright, which goes through the math and tries to do this with data that were available 20 years ago, and is not very successful because it turns out that if you don't have a north-south measurement, a measurement that's sensitive to north-south motion, you really can't separate it out. And then there's a paper of mine, which is pretty much a follow-on from that, where we have north-south measurements from pixel offsets of an earthquake, and we include those, and then you can solve for all 3 components. So read those papers if you want to know more. And also the uncertainties are calculated in those and tells you how to do that. Someone asked about that as well.
I want to put up a plug for that the 2005 paper. It's got very nice images in it too that walk you through what's going on, maybe better than the other ones do. Good job, Gareth.
That's
I
from
still
my
use.
PhD.
There's a question about how can you improve anything if you have GNSS data? Possibly, but again, you have GNSS data at only a few points. If you truly feel that you could interpolate between those GNSS points and use those interpolated data sets as a different, pseudo data, then that would be one way of doing it. The thing I talked about before, where you basically include elastic constraints, that could easily use the GNSS data as well. But that sort of approach won't work for surface breaking faults or things where there's anelastic deformation going on. Yes, and this is about the sensitivity. The fact that those north-south components of the vectors is much smaller than the other two does mean that any noise in the data is going to become a larger noise on that component. So even if you have, say, overlapping ascending tracks and a descending track, hey, maybe even 2 descending tracks. There are places on the world where with Sentinel, you have 4 different line of sights, 2 ascending that overlap and 2 descending, lots of little diamond-shaped areas. Even then, you can definitely solve for the north component, but it'll be much, much noisier than the east-west or the vertical. And it is very hard to launch a satellite into a non-polar orbit.
But we have UAVSAR in the US anyway, which is a plane with a radar on it, and you can fly that in any direction you want. And so in certain places in California, we have quite nice complementary UAVSAR data sets that allow you to do this 3-dimensional decomposition. That's what one of my students is working on.
By hard, I don't mean it's hard to launch it into that orbit. It's you wouldn't get the coverage we want to have with polar orbits.
One of the things about the polar orbit that these satellites are in is that it maximizes the amount of time that the satellite spends in the sun collecting solar power. So that's partly why you want your satellite to be sun synchronous and polar, is that you maximize your duty cycle, the amount of power you get.
Any other questions on this front? I'm going to stop sharing. Oh, wait, maybe I won't. Maybe I will share my.
Yeah, talk about more soil moisture.
Nonlinear velocities. Well, then you have to do something more like what Gareth is describing, instead of just having an average rate. So imagine at every single point you have some sort of signal, right? You have some sort of displacement versus time. For nonlinear, you could, instead of fitting a line to that, you could fit a nonlinear function if you actually knew what that was, say a post-seismic signal. But if you're, say, looking for transient deformation, like for a landslide, then your best bet is to break your time series into a bunch of small chunks, have a linear rate in each of those. That's kind of what Gareth was describing with like having a moving window and doing the same sort of procedure in each time step.
Yeah, so you've got 20 minutes or 10 minutes to talk about this if you wish.
I need to swap my displays. Okay. I'll
This
get through
looks
this.
good. Yep.
Just a bunch of people have worked on this part of the mission. And so this is basically just going to describe a really high level overview of what is going into the NISAR soil moisture product, as well as how we're trying to figure out, do we actually know the answer or not, and how you might use it. All right, so again, NISAR itself, as everyone has already mentioned, has these 4 main areas, including applications and disaster response and things like that. Soil moisture is the only one that's what we call a level 3 product, which means it's just derived at a more derived product than the other ones. And so there's lots of things one might care about, depending on what your problem is. Soil moisture people like to know what the soil moisture is, obviously. Personally, as more of a solid earth deformation person, I'm interested in things like, what is the state of soil moisture on landslides and how does that affect how they move? We've seen lots of cases where variations in soil moisture, vegetation, water content affect the interferograms in ways we don't fully understand. And so again, having more information about what the soil moisture is, maybe derived from the data itself, could be useful. And so the very basic way we get soil moisture from SAR is not, for the models we're going to talk about today, it's not from the phase. So it's a totally different dimension of the data than you've been talking about most of this week. It's basically how bright does the surface look. And so if you have very dry soils, these are figures from Rowan, who I think is on here. Hi, Rowan. You have basically a lower contrast in the dielectric constant between the air and the soil itself. And you don't have as large of a reflection from the ground surface. If the soils are wetter, you get more of a response from that surface, and the ground overall is going to look brighter. Right? This is very, very broad brush. There's also issues like vegetation change, right? And that will complicate all of this. So, but on very, very first order, one would hope that when the soils are dry, they look dark. When they're wet, they look brighter. And that's what we were seeing for that example in England I showed you earlier. And so again, really first order, what this brightness is sensitive to is mostly surface roughness. So this is images of Okmok volcano in Alaska, where I think we've seen some data from this already today. And again, rough surfaces that are leaning towards the satellite, at first order, that's going to dominate how bright the satellite data is. And so because of that, a lot of the soil moisture estimates come from looking at how does something change over time. So you've got one pixel that could be brighter or darker on average. We care about whether it's getting darker or brighter from day to day. Okay. And so, but there's other things going on. So this is just looking at some of the very first NISAR data we had. And I still like this animation because it shows that the NISAR data itself can constrain soil moisture. And so what's shown here on the left is just the copole horizontal brightness on, I think, five or six different dates, starting in kind of November of 2025. And so here's San Francisco up here. This is just how bright the image is in dB. And on this date where the rain symbol pops up, I hope you can see on the left that it gets brighter, right? It's dark, dark, dark. There's a lot of variability in the image, but overall the image gets brighter. Oh, and I crashed. I hear you. Let me see if I can pull that up again. Anyway, that was the main thing I wanted to show. I think I will stop sharing and see if I can come that up. But the key thing with soil moisture that I can just tell you is that there are 3 different algorithms. And if you open up the product, you're going to see, if you kind of look at the kind of tree of files and layers, you'll see algorithm candidates. And there's 3 different algorithms. And they each are derived from totally different sets of kind of auxiliary data. So one of them only uses one image at a time, and it makes a very coarse resolution of estimate of soil moisture, and then basically uses the high resolution InSAR data to roughen it up, right? So that one's going to be really good at seeing, is this one field wetter or drier than its neighbors? Another one is, the other 2 both use time series, so they use more than one date, and they're looking at basically, is this image getting brighter or darker over time? One of them basically constrains those brightness changes to the range from the SMAP mission. So at every single location on the Earth's surface, it has this pre-existing data set of, on average for that 2-week period, what's the soil moisture? And so it'll kind of constrain the NISAR soil moisture model to be within that range. And the third one is kind of a physics-based approach where they've actually forward predicted how bright the surface should look like given a certain amount of vegetation, what these different polarizations should look like. And it uses that information to kind of pull what the soil moisture should be. That one is using the average vegetation content of each pixel over the course of a year. So if you have an area that just burned, or a person who just started a new agricultural field that was not an agricultural field in the past, that model will have a harder time than in a place where you're kind of seeing the same thing from year to year. So right now, the soil moisture product that you look at, it'll have a top level layer that says soil moisture. It's the first thing you see, and that's the average of those three. So the idea being that they each have their different strengths and weaknesses. If you average them together, you're kind of minimizing many of those differences. But for some of them, if you want to say, look at an extreme event, one of those models might be better at that than the others. Whereas something where you're just looking at maybe short spatial scale changes in an area that is kind of always do the same thing, then one of the other models might be useful too. So that's why we left 3 layers in there for everyone to look at. We were just thinking that the real community that starts looking at this might find that one of them is more useful to their needs than the other. Can we use the soil product to detect irrigation? Yes, that's one of the main things. When you really zoom in, that's really where it does well. You can see the center pivot agricultural fields all over the Western US. They show up really well in the Nile Delta in Egypt. For NISAR, the scale, we can see those individual fields really, really well. Whereas if you look at, say, the SMAP mission with a much, much coarser spatial scale, it's not very good at seeing those smaller scale features. So I think that's one of the places where NISAR is going to do really well. It's giving you really global pictures of what is going on in irrigated fields. The side thing to that is that these different models have different ways of trying to remove the vegetation component, right? We're seeing, is the ground getting brighter or darker? That's going to be a combination of soil moisture and vegetation. And so for certain types of crops like corn, when you're at kind of the peak of corn, right before it starts to dry out, you're not seeing the ground. If you've ever tried to walk through a cornfield at that point in time, you can't force your way through it. My husband has a farm in Illinois, so I've experienced this firsthand. And so there are crops where when they get to that extent, NISAR and really any microwave imaging isn't going to be telling you much about the ground surface. So you have to, like with anything, you have to take some care. HH and HV are used for 2 of the algorithms. One of them uses HH and VV where it's available. So that only works in the quad pole areas and uses HH otherwise. Okay, urban areas, we don't try. Actually, what's done is things that are marked as urban on a land cover map are actually masked out of the data. But if you look at, say, a city like Los Angeles or San Francisco, it's a 200-meter grid we're using. And so things like city parks and areas that have a lot of greenery in them are still used. One of the problems with our product there, though, is that even with the RFI corrections, cities are very bright, and there's a lot of other things that contribute to the backscatter at any one little location. So I would still be a little careful about trying to, say, figure out what the soil moisture is in Golden Gate Park. Can I use the soil moisture to improve the coherence in my AOI? That's getting closer into what my actual area of research is. There are quite a few efforts around the world right now to try to better understand the effect on phase from soil moisture. And the answer is yes, but it's really, there's no canned notebook that you could just use at the current time. Is Simon's Zui back on today? He's one of the world experts in this, and he's been on a few of these calls. But yeah, there's ways of basically looking at the combination of phase and backscatter and looking at the history of that, and also looking at how the phase statistics are varying over short spatial scales. And so if you've had any discussion of phase misclosure, which is like if you have 3 different dates and you make A to B, B to C, and A to C, those 3 interferograms, if they've been filtered or downsampled, won't actually add up in a consistent way. If you do them at full resolution with no filtering, they do, by definition. But when you filter them, because you're filtering a complex number, it's not a linear process. And what you learn about from that is stuff about what does the statistics of the phase look like. If the distribution has like a skewness to it, you'll end up with these kind of biases that people have talked about. And so there's a whole bunch of ways to try to correct those. I have a paper, if you look up my name and look up Oman is in there as well, where we were looking at a place where the only thing going on is rain in a fairly unvegetated area, and it's dry most of the time. You can then try to improve coherence by having a correction for what the soil moisture effects would be. And that's by basically having a pixel to pixel correction. But it's really something you can only do in the most arid places where most of the time it's not raining. Okay, so hopefully that answers. Any other questions?
I think Yunjin will be talking about phase closure in the MintPy lectures.
Yeah, I was hoping that would come up.
We will have more. I think we are done for the morning, Pacific time. Thanks, Rowena. That was awesome. And you did manage to fill your time. We will come back, I think, after a short break at noon Pacific, and we'll start the discussion of InSAR time series. Welcome back, everyone, if you did indeed come back. Next up, we have InSAR time series theory, and I see both Anne and Scott are here. So one or other or both of them will be telling us about InSAR time series, which is what we all came for, right? I feel like.
Yeah, I think I'm gonna get started with a quick overview on what is going on behind just a simple InSAR time series example. Then I will leave it to Scott to handle some more latest algorithm. Okay, let me share my screen. Can everyone see it?
Yes.
Okay, let's get it started. So this is again with contribution from many people here, and you have seen actually many of them are in this year's class. So let's just have a quick review of what actually InSAR measures, right? And so I tend to think what InSAR do when you have a single interferogram at a given pixel, what it measures is the amount of total deformation that occurs between the two SAR acquisition time along the radar line of sight direction. So what we're measuring here, what you're measuring is the phase difference, which is can be translated to deformation along the radar line of sight. And the line of sight direction here is from the satellite to the ground. Some processor, their definition is from the ground to the satellite, and so you always need to check their line of sight definition. So don't be surprised like some processor, they give you an opposite sign of a phase if they're adopting a different line of sight definition. And as long as you're consistent, internally consistent with line of sight deformation, you should get a consistent deformation result at the end. So this is what we measure, right? And so that is why if the signal is big, just remember not only we have the deformation signal in it, there's also noise. So if you have a co-seismic interferogram, when you form a co-seismic interferogram, which means one of the SAR acquisition happens before the earthquake, and one SAR acquisition occurred after the earthquake. So you form this interferogram, it records the amount of deformation occurred during this 2 period of time that including earthquake. And because the earthquake moves so much, it's bigger than a lot of the noise terms. So you don't really need a time series analysis. You form an interferogram and you will see these nice fringes related to, for example, big earthquake, volcanic eruption. And your map should be if you do a scale, it should be deformations unit, that's centimeter or meters in some crazy case, and the direction without doing further decomposition is in line of sight. However, in most of the case, once we have learned to form an interferogram imaging earthquake, which happens, but there are many use cases people are interested in deformation analysis. And in this case, a lot of the time, you're interested in maybe a very small transient motion or maybe a secular motion, right? And so they're usually very small, like often millimeter to centimeter level. And at that time, when you form an interferogram, that signal is too small. What you're mostly seeing in those interferogram are centimeter level noise that are dominant in your data. And in this case, what do we do? And intuitive way. It's just collecting more noisy measurement. And perhaps once we have 10 noisy measurement, we can make one single estimate that is more accurate than any of them. So InSAR time series is a framework that allows you to take the information that get from a stack of interferograms that spans different time, and then through inversion to solve for the true deformation time series like that. So let's just illustrate a very simple example here. So here the line in red is just an illustration of perhaps a true signal. It's in this case a synthetic case, which contains a secular motion and also a transient motion in the middle, right? And those blue dots are our SAR acquisition measurement, right? And available SAR acquisition. And then remember, those blue points are like not exactly fall onto the red line. It's because we have noise in it. Just remember, each of the measurement maybe it's a little different, right? And when we are forming an interferogram using the SAR data acquired at T2 and another SAR data acquired at T4, and that's what we measure. And what we can do is we can actually try to write it in terms of the things we're interested in. That's the velocity between each SAR acquisition time, right? If you know the velocity, then you multiply the amount of time, that is the total amount of deformation over that time. So since we expand like 2 delta T time T2 and T3, so we write velocity V2 times delta T32, and then there's another velocity term, we lose the second term, and then plus a noise term, right? So that's what we measure. And in this particular case, delta phi is what we know. V2, V3 are unknowns, but that's okay. This is just an equation that we derive from a single interferogram at a particular pixel of interest. By the way, since we know when those SAR positions are acquired, you know T3, T2, T4, and T. So those are known constant that you can calculate based on which day this SAR data are acquired, right? And now, if we have, in this case, a SAR acquisition, so the total amount of a velocity interval is 6, right? You have a 7 point, there are 6 intervals in it, and we're interested in the average velocity between these 6 intervals. So there are unknowns V1, V2, V3, V4, up to V6. And we can form M small baseline interferogram. I will talk about what is a small baseline interferogram in a second. But this M actually has a constraint. So theoretically, you can form an interferogram using any of the 2 dots, right? So the maximum number possible interferogram you can get from 7 is 7 choose 2. Right? Interferogram 1, 2, and interferogram 2, 1 contain duplicated information, just the flipped sign, right? So, so if we're just using the unique pair, it's 7 choose 2, right? So M is going to be smaller than that number. And typically, we use a threshold to say we don't want an interferogram that spans too large of a time, because if they're decorrelated, they don't contain this useful information. They become random noise, right? So small baseline interferogram techniques is basically a simple way for you to select interferogram with reasonably high quality data, exclude the one that has completely corrupted by decorrelation noise. So we'll have an M interferogram that you can actually, once you have usually a good way to do is trying to select a temporal baseline threshold, look at the subset of interferogram, are they decorrelated? If they are all very coherent, you can probably set the baseline threshold to be a little larger, right? And if you start to set it to too large, then you'll see a complete a portion of interferogram are decorrelated, then you set it to be a smaller value. And depending on your temporal baseline threshold, this M will vary. So for each of the interferogram at this pixel, you have one equation like the one we see here. So in total, we are going to have an M equation. Usually, we are going to have more than 6 interferogram, right? Because there are so many possibilities. We have M equations, 6 unknowns, and we can actually solve these unknowns using least square or any other optimization approach. And here is just instead of writing them as a single a set of equations, we write it in a compact matrix form. So this B matrix contains all those time information. This delta phi is our data vector. And this V is what we can solve through least square inversion. And once you get the V, you have several options. You could integrate the V over time. And since we know the delta intervals, then you get the deformation time theory, right? And sometimes you will see if this tropospheric noise are too large, your time theory will be pretty jumpy, right? Then you can say we want to use maybe form additional, maybe fit a line across these noisy time series to better estimate the trend. So that's what we call a linear deformation model once you have these time series. So you can apply different deformation model based on your prior information. And so that's the basic idea. So one of the problem here, I think the basic idea is very simple. So why sometimes InSAR works great and sometimes we struggle? I think if you haven't seen enough interferogram, a very common thing a new student like made is they underestimate how noisy your data is. So if this is actually a very good case in this illustration, right? And the black dots are still following it. But in reality, for example, if you have 1 centimeter per year secular motion, right? And you have 1 month interferogram, 36 days, a little over a month. Like think about how much deformation signal are there in those interferogram, right? 1 centimeter per year, then divided by 10. It's like a very tiny, small deformation signal in each of those measurements. Well, most of the time, there are many noise term that included that is on the order of centimeter or larger. That's why we need a lot of interferogram over a long time. Even with that, sometimes you have to be careful and understand that once you get a solution, you feed a set of interferogram, you run the time series, MintPy can do that. If you have a good signal to noise ratio, you will get a very reliable solution. But if your signal is small or your data quality is poor, and then you will get a poor solution. So what are these noises? So we need to better understand them and then have a better strategy to deal with them. So in most of the cases I have looked at, I'm mostly working with two things, and they kind of have a competing effect on them. So the very first one is decorrelation, which is a problem when you start to see some like a decorrelated area in the vegetated terrain over longer baseline interferogram, right? And so, usually when decorrelation happens, the impact is it's going to be very hard to do the phase unwrapping, and you can introduce in phase unwrapping error. So these two things are usually related. When you don't have decorrelation coherent, typically there's going to be very minimal phase unwrapping error. But when you have severe decorrelation, and the phase unwrapping error going to be large. And the phase unwrapping error, once it's introduced, it's hard. How big it is. When you're making a cycle of error, it's going to be at least 2 pi or 4 pi or 6 pi. So for C-band, each time you made an error, it's going to be at least 2.8 centimeter of a error you introduce. So you don't want to have a lot of those input you feed into the inversion has large phase unwrapping error. And I think Scott's gonna talk about techniques that better deal with that. And another component is the tropospheric noise. And we have talked about we can use the Geico's and a better European weather model to remove the stratified component. But in a lot of the cases when your area is very flat and a lot of them are turbulence noise, so that is like a changing within hours. So these are kind of a random localized component that is hard to be captured by the weather model. And a lot of my case that end up being the residual noise pattern in the final deformation solution. So effective strategy is if you have a secular motion, you require 3 years of data, and then you have those noisy measurement, you fit it to a trend. The longer this time series is, and the more accurate your solution is, which is essentially has this requirement, have a more measurement over time, right? And then hopefully the noise gonna cancel each other out, right? And so that's one method that we do. But unfortunately, sometimes in the decorrelated region, if you end up have to throw away a lot of the decorrelated interferogram, then that limits the number of interferogram you can use for that averaging. So give you an example of these two competing factors. And by the way, I forgot to mention, so for the C-band Sentinel data, unless you're working in high latitude region, that's not a concern. because they're they're more prone to like L-band data. For the L-band, the NISAR data, typically before you do the time series inversion, you want to at least mitigate the ionosphere, because right now we're in solar maximum. So if you don't mitigate the ionosphere, that's probably the first order. The largest fringe pattern is all from ionosphere, and all the other term probably is a secondary order. So these are the decorrelation noise we kind of show up over Sentinel data over Gulf Coast, where you see this nice coherent fringe pattern. That's the Houston downtown area where you don't have a lot of trees. Typically, this area, they don't decorrelate too much. So even over multiple years, you can get coherent phase pattern. And you zoom in, what is really coherent, right? You zoom in, which just means when you see coherent measurement, which means when you have a yellow pixel, it has a very high likely chance that the neighboring pixel is also yellow, and they kind of vary slowly in space. That's the nature of the tropospheric noise or deformation pattern, because in most of the time, Earth is an elastic medium, right? And so when aquifer deform, they tend to have this low wavelength signal over a broader region, unless like there are some like localized sinkholes, and they might see some very localized variation, right? So they're usually very consistent over space. And if you have severe decorrelation, when do you know that interferogram need to be thrown away? Is when you zoom in, it looks like a broken monitor. So this is just random phase patterns, and there's no useful information for time series analysis. If you include a small percent of this decorrelated measurement in the SBAS, that's probably okay. But when you include in a large amount of the input data looks like decorrelated, you're not going to get a valid deformation solution. And how do we deal with this and get a more reliable solution based on this basic idea? I will leave Scott to talk more about more latest development. Okay. I'll share.
Before Scott gets into his piece, do we have any questions at this stage from anyone? Doesn't look like it. Okay, Scott, feel free to share.
Okay. We can see the correct, not the speaker. Okay.
Yep, sounds good. Looks good.
All right. Yeah, I like that present. So I guess I'm also presenting slides where a lot of them were Haresh developed since for, I don't know, 6 to 9 years. And last year I gave this talk. So these are a few updates from last year, but it's a good segue because a lot of InSAR time series theory, it can seem very complicated, and it can be hard to get the justification of why you're adding this complication, especially when you get so much information out of like single interferogram sometimes, or NISAR is so coherent all the time. The time series theory that I'm going to talk about is mostly how to deal with decorrelation noise. And to do that, we're going to go back a little bit to some scattering theory that we did in either the pre-course or maybe lecture 1 for the radar underlying theory. And then we'll talk about a few new modern techniques like phase linking, which can be shown to be kind of like a filter that works well to mitigate decorrelation and can just make downstream time series theory a lot easier. So another confusing aspect is that you hear time series theory as a way to separate deformation from atmospheric noise, and that is one part of time series theory. And depending on your study area, that can be the entire aspect. But in other cases, if you mitigate decorrelation noise, then you basically already have your answer. So one way to view this is to say the input to time series analysis is a set of co-registered co-registered SLCs. For ISCE2, the stack processors, they were using radar coordinates. We've now seen how pleasant it can be to have geocoded SLCs, and especially for NISAR, I think a lot of you will want to use those, that they're already co-registered and they're already on geographic coordinates. So you can pop them into your time series analysis box and output the same number of displacement epochs. So these will be relative in time to one date, usually the first date, and they'll be relative in space. So this is that line of sight output. There's an arbitrary reference point that you pick that hopefully is correctly 0 deformation. And at each pixel, you get something that looks like this on the left, where you can plot the pixel over time, and you've picked a 0 time point. And if you've picked your 0 space point correctly, then this will be how the ground has moved toward or away from your radar. So the way people get to that answer has changed over the years. And to understand the PS versus DS, so persistent scatter versus distributed scatter, it's helpful to see what early data looked like and how people were viewing the problem. So if you've heard of the term PS, persistent scatterer, that is an abstraction, but it's a very useful one. It is basically how people have modeled that each radar pixel in the single look complex image is the sum of many scatterers within that area. So if it's Sentinel-1, the pixel size is about 3 by 14. For NISAR, higher bandwidth, it can be only 5 by 5, but everything within that 5 by 5 will contribute some amount of radar scatter back, and they coherently add up. And so the way people often plot coherent adding is to plot the complex numbers, or a phasor diagram like you see here. And the idea of a PS pixel is that you say there's something in there that's very stable and reflects a lot of energy back. And so that's that blue part of, the black is the signal that you care. And then all those other little parts, they contribute less, and they're called often the clutter. And so when you add up all of these scatterers together, the noise walks along that red path, and you get something that ends up looking like that blue. So if you could ideally measure just the signal, it would be 0 phase is what I've zeroed it arbitrarily. Instead, you measure something with noise, and it's about 9-10 degrees of error. And so that's like your single pixel error. So for a lot of cases, that's actually pretty low. And so if you just find in the image pixels that have some very bright pixel, very bright scatterer, only use those, you'll have interferograms that have very low noise. And the downside is that these are sparse. The alternative to this is if there's not something really bright, people call it a distributed scatterer. So everything within that pixel kind of equally contributes. So if you add all up the complex returns and plot it on the left, you want something that should be 0, but all the noise roughly adds up. And so your phase error, so the angle from the 0, is very large here. So that's 140 degrees, or almost a quarter of the radians away down from it'll look like pure random noise if you plot a lot of these together. And what multi-looking does, when you have formed those interferograms that you did yesterday, you're basically adding up a lot of these distributed scatter pixels, and you're assuming that the signal within them is roughly the same, and you can average out the noise by adding these together. And so you get what kind of looks like a longer winding path where the signals all point in the same direction to the right. The noises point in different direction, and the composite scatter is less noisy. So the trade-off is now you have a coarser pixel because you added a bunch. So now you kind of took a rectangular window and that's your output. The benefit is it's noisy and you can actually hopefully interpret something out of it. People were more interested at first in PS time series. So in the early 2000s, this is from the Ferretti paper that he put out, the kind of the theory and successful examples where he came up with a very simple heuristic to find within a SAR image which are the not so noisy pixels. And the interesting thing that he found was that if you only look at the lowest noise pixels, the brightness of the pixels is going to be correlated with how low the noise is. And so you can form this very simple statistic from amplitudes only, which will also tell you that the phases are not so noisy. So this sigma over mean, he called it amplitude dispersion. It's also the coefficient of variation. So this is like a pretty common statistical quantity used elsewhere. And it just says you have a quantity, a stack of images over time or something over time. You want something where there's low standard deviation and large mean or brightness. And so when amplitude dispersion is low, you have a PS pixel. I'm not going to go into the equations here. These are on the slides, but people wanted to improve on this because it was pretty sparse if you only look at amplitudes. And so other people like Andy Hooper started to look at phase-based, where you look at more than just the amplitudes. Piyush Akram also came up with improved like signal to clutter measurements. They all were going for the same thing of I want these like low noise pixels, but I'm willing to accept a little bit more noise if I have a lot more spatial density. Sorry, this is the Piyush method. So a lot of them used low-level probability theory for what we expect the radar to look like if we have this modeled backscatter, and then they come up with something like, okay, we'll come up with this cutoff for this certain metric and pick those pixels. And then a more recent one is rather than just the amplitudes, Ko Wong from our group, he had something where he's looking at just the similarity in nearby pixels, and if they have similar phases in a way that's easy to calculate using just a cosine similarity that's popular in machine learning now, then you can say these are lower noise pixels, or they agree with their neighbors more. And so it's somewhat of a heuristic approach, but it's kind of exactly what you want to be able to unwrap correctly. That if you know a pixel looks like its neighbors, when you spatially unwrap in 2D, then you're going to mostly agree and have clean unwrapping results. To illustrate what the amplitude-based ones look like, this is over Miami, so the southeast coast of Florida, if you're not familiar with it. The optical is on the left. If here I took a stack of 160 SLCs, and I took just the amplitudes and took the standard deviation, divided it by the average mean, and then you get that image in the middle. So over on the right is where the water is, and so there's high values. That's high amplitude dispersion, because every day it's random scattering from the ocean, so you get pretty noisy stuff. And then over the neighborhoods, that's where you're going to find the PS pixels, the dark ones. And so to get this PS map, you just take a threshold and say, whatever noise I'm willing to deal with, I'll pick those. So it's very simple. The problem with it is, I mean, you probably don't want to process golf courses, but you can see, for example, agricultural areas are going to have little and often no amplitude-based pixels, even if sometimes you can get a usable signal out of it from averaging DS pixels. So people were interested in using more than just the PS pixels, and this is the core idea behind SBAS in the original paper. I like Anne's presentation of like the core idea of using multiple redundant measurements, phrasing it as a linear system, and then solving for your unknowns. The way they often did it is we'll plot the perpendicular baseline, because missions in the in the late 90s and early 2000s, it was more difficult to control the orbits. So there was a real problem of if your perpendicular baseline was too big, you know you're going to have decorrelation. And so you should just not even try to form those interferograms. And so they made graphs that look like this of just trying to pick things. We expect a certain amount of decorrelation if the dots, which are SLC images, are separated vertically. We also expect decorrelation if they're separated over time. So we'll pick ones that are short baseline in both regards. And then you can just form interferograms, multi-look them, and now you've got just a stack of interferograms that are overdetermined. Each one of them has noise, and so you can solve some linear system and figure out what your residuals are, which can be called temporal coherence. I think that's what MintPy calls it. And there's a variety of ways you can solve it too with L1 norm or L2 norm. Yunjin is going to talk about this more, especially that you can walk through the MintPy code to see how they do it. And this is a very like nice and simple way, and you should code it up for yourself at some point to understand this. So then why did people start to do phase linking? There are times where you want to solve the misclosure problem, which if you go back here and look, if you form interferograms that are short in time and space, and then you look at triplets, so interferogram from day 1 to 2, if you add the phase from day 2 to 3, and then subtract 3 to 1, if there were no noise, it would be 0. But if you do this with real interferograms, you'll find that it doesn't close. So that was one of the impetuses from starting phase linking, which is what if we, instead of unwrapping everything where we know there's noisy, and then we're going to solve kind of the phase noise and the unwrapping errors together in this linear system, what if we first optimize the best wrapped phase we can do? And so the way they pose this problem is we're going to form all interferograms. Some of them will be very noisy. And then we'll do some optimization scheme and try and get the best wrapped phases. And we're also going to solve this misclosure problem so that we'll basically have the same thing as a PS pixel where if you take single look pixels, there's no misclosure. And so you know that you can form interferograms, and the only reason you'd form redundant ones is to unwrap more easily. But you're going to get a cleaner phase, ideally, and it'll be easier to unwrap. So the way people do this is, another way to look at this is forming the coherence matrix or the covariance matrix if you didn't normalize. So at every pixel, you've taken your stack of SAR images. Here I'm saying you have n SAR images. And that means you can form interferograms from any pairs. And so you have an n by n coherence matrix. To form this, you multi-look in a window. So you take what is ideally homogeneous pixels in a little area, multi-look to get an interferogram, and then fill in the coherence matrix. So I'm plotting if you divide by power in the way that was that same interferogram formula that Haresh presented, you've normalized so that the amplitudes go from 0 to 1, and that's the correlation of your interferograms. And then the angles of this complex matrix are the phases. So this is the pixel view of the coherence stack. And you read it off by saying, if I have row 1 and column 3, the amplitude of that is the correlation for the interferogram 1 to 3. And the phase of that will be the angle of my interferogram from day 1 to day 3. The spatial view, so now that's like 1 pixel. If you instead look at what it does after you've done this optimization, because some of you are going to look at this and say, this looks a lot kind of like Goldstein filtering. So you've taken an interferogram, it's kind of noisy. You apply a filter to that interferogram, and then you get something cleaner and easier to unwrap. To show how this is different, I'll start with a synthetic example where you can kind of simulate turbulence noise. MintPy, this is in MintPy 2. I used a different package that is able to do this kind of quickly at large stacks. So you can add turbulence noise. You can also add decaying decorrelation noise. So I did a stack of 60 days, and over time it will decay like this exponential relationship. So I have a time constant of 60 days. So I'm simulating as low as Sentinel-1, so it's every 12 days. And after 60 times 12, you don't expect to have coherence. Like it's going to decay to 0. But after 1 month, you can still form interferograms, and you don't even have to multi-look very much for it to be reasonable. So I'm showing both 3x3 looks, where it's still high resolution and doesn't look that noisy here, or the 12x12 where it becomes coarser, but ideally cleaner. In this one, I'm Goldstein filtering the 12x12. So I'm Goldstein filtering the column to the right. And this is the output of phase linking. So I've taken that full stack, run phase linking on it, and now I reform the interferograms, and they're going to look like normal interferograms, but they're going to look cleaner. And so you can get one idea that is the way some people like to do this is they do it at every single pixel. So you retain the same output posting. They sometimes call it output or full resolution, but it's really full posting because you have multi-looked. So you've correlated the output. As you look at longer and longer time baselines for this stack, so now I'm looking 4 months out, you start to not be able to take a small number of looks. So 3x3 becomes very noisy. You probably don't want to use that. In this case, the 12x12 still looks okay, and especially after Goldstein filtering, like kind of looks, Goldstein filtering sometimes changes the phase and makes it strange, but it's definitely cleaner and easy to unwrap. But the phase linking still looks fine and looks like almost like there's no noise, that it has been able to extract the signal away from the noise. And by signal here, I'm talking about phase from the atmosphere and from the deformation that I've added. This phase linking does not solve any turbulence from troposphere noise or any kind of ionosphere or atmospheric noise. It simply is dealing with decorrelation noise. But what it does give you is after 12 months, both of the normal multi-looked interferograms start to look like pure noise because your exponential decay has gone way down. And if you put a super noisy interferogram into a Goldstein filter, you come out with super noisy interferograms. But phase linking is able to recover this. And now at this point, you may ask, okay, you did a simulated example. That's nice. Does this actually work? So this is a stack of X-band data. So there's a spotlight stack on the Capella's open data archive of Palos Verdes. So in this area, there's a landslide. The polygons are from Al Handwerker. That they've kind of mapped the historic landslide area as well as the recent, the 2023 acceleration area. And even after 21 days for the shorter wavelength, the X-band starts to look very noisy. But if I take the full, if I take 15 SLCs and run phase linking on it, that same interferogram looks like this. And so it's actually pretty immediately usable. You can see the clearly the still moving area, as well as it's changed because these polygons were made from 2022 or 2023. And now this was taken at the end of 2025 or end of 2024. No, 2025. We're in the year of 2026. So yeah, this is a pretty striking demonstration. It kind of becomes more striking at X-band, and then C-band is still true. NISAR, we're going to have to go further away. Like NISAR is so coherent that in some cases, like you're not going to see dramatic differences like this in the coherence. I'm going to leave a lot of the details about the optimization algorithms. So I've been saying like you run it into phase linking, and I didn't say how you do that. The simplest way is this number 2, and that's where you take that coherence matrix and then do the same thing that principal component analysis does. So if you've taken a data science course and done PCA, you basically take the strongest eigenvector, and that is literally all that algorithm is. You take the InSAR coherence matrix and then take the biggest eigenvector, and that's what you output. So in summary, why you might do this is you can decrease noise and lead to less parameter tuning, because a lot of people's, not everyone's, but many SBAS pipelines will be very fiddly to the temporal baseline and perpendicular baseline thresholds that you have. That if you change the network, it can pretty drastically change the final velocity results. And this will actually, this will decrease the amount that it changes by a lot. That if you run phase linking, you can choose what set of interferograms you want to unwrap to get the final displacement, but it can be a lot less fiddly. And in fact, that's why for OPERA, we were able to do this and then just say, unwrap the nearest 3, and it works in a very large portion of cases. And it's not that expensive if you implement it well, and we've had time to implement it well, so it actually runs pretty quickly. I'll leave this here as the reference difference of kind of the pipelines from phase linking versus SBAS, where the main one is you have this step to make things PS-like, and then you can unwrap some network if needed, or in some cases, you don't even need a network, and you can just unwrap single reference interferograms, and you have your displacement. We're also not going to go into the mini stack. So another detail about how to do it for if you have 300 SLCs, it's pretty expensive to form the covariance matrix for 300 by 300 and then solve it. So Homansari came up with this pretty nice way of handling that. You just form kind of batches, and then you do this little compression step. They call it a compressed SLC. It's kind of strange. It's one way to handle it. It's not the only way, but it's also the way that Opera did to form small mini stacks, solve them, and then have it running over time. And it dramatically cuts down the runtime without often sacrificing much performance. Because if you think of forming a 300 stack of SLCs, most of the information is in the short baseline ones. Like after a year, you're not going to get much more by forming that interferogram of pure noise. And so if you've also heard kind of combined PS-DS algorithms, the combination is literally just like running this phase linking step and then also calculating some kind of PS selection algorithm. And if you say, oh, we really trust the PS pixels, so in the output, you just insert the phases from the PS pixels and overwrite the phase linking outputs. So yeah, a lot of these other slides are kind of cool applications that these are Haresh's first demos of what you can get in terms of improved coverage over the California fault system, and you can get nice resolved time series. Yunjin will show you how to get these from MintPy. You can take another cool application of the coherence matrices is that they can be inputs to change detection algorithms. So this is like one of the coolest visual examples where if you just formed the coherence matrix and like plotted it at a pixel, you can see where the earthquake happened, because everything before to after is going to have low coherence when there's a giant rupture and the surface has shifted. But in each side, so all the before to before and after to afters, like they still form valid interferograms. And so you can come up with ways to have detection algorithms or machine learning algorithms that take these coherence matrices. And how Opera is using it, we have, I guess these are kind of pre-release slides where on the left is Brett Bazanga's Houston, Texas study that he has it and gets good coverage around the greater Houston area. You can get pretty good Palos Verdes landslides. There's another one, although this is kind of a funny example that you can track the data, but Sentinel is an example where you don't really fully resolve the Palos Verdes. So you can see it coming, but then when it really accelerates, Sentinel doesn't revisit fast enough. But as I was saying, of the benefit of like, why do I like to use phase linking is that some of these large scale, like the middle one is Marin Gaborchin, who's like heading up the VLM project. This was his VLM over California. And he spent 1 to 2 years of his postdoc, like manually getting good time series correctly. And the one on the left was, and then the one on the right was from Xiaohua Xu, that he had one of the first like full California maps that was also like hand tuned to make sure that all of the areas looked okay. And then the one on the left was like running it through a pipeline. So we're going to look how to run Dolphin yourself, but that was like downloading for this Southern California area. We didn't have to throw away days, and you run phase linking, unwraps it. It comes out with a nice clean time series, and then we just fit a line through it. Where am I? Oh, sorry. The main differences here are where we didn't throw away or try to filter out time series or co-seismic signals. So MintPy is able to do that. So if you want to use that, you can look at this time series and then fit the step function at the correct date. And in fact, this is what it looks like for the ascending pass of North America. That this was another taking the granules from Opera displacement, fitting just a line through them, and then trying to solve for some offset to do long tracks. So this wasn't actually even with troposphere corrections or ionosphere corrections, because they didn't make a huge difference here. This was just line fitting and then offset solving. You get a pretty cool map. And also, as I was saying, it's not terribly computationally expensive. That we got, because we've now processed this data, we have a good set of run times of kind of a benchmark. If you want to try a new algorithm, like you can see if it performs better, and then you can also compare how long it takes to run. On the right is the colors by the total runtime of a single mini stack. So we'll input 20 dates to each Opera service displacement kind of like product run. And this is in historic mode as we're working through the Sentinel archive, and then it'll pop out 20 new displacement epochs to store as granules in the ASF. The runtimes here, this is from the paper that came out this year. If the total runtime mean is like 6.7 hours, then the phase unwrapping step using Snafu was taking like 5 to 5.5 of that. So the pink ones where there's even more higher runtimes, kind of in the middle of the country, and especially in the decorrelated areas, that was mostly more noise leads to bigger runtimes. But the phase linking was not the bottleneck here, that it very consistently took an hour and a half for the whole frame. And yeah, actually they might, so I've posted a few times to random people, but I've been trying to get up a new phase unwrapper that's based on work that our colleague who was working on Opera, Jeff Gunter, he had a very cool, simple prototype of a nice algorithm. that was trying to be simpler for smooth unwrapping that we're doing for displacement. And then I have been using AI tools to make it alive again because he's now at Array Labs and is not working on phase unwrapping, even though we wanted him to finish it off. And it seems to be running a lot faster. So phase unwrapping may become less of a bottleneck. And then who knows, maybe we'll have to go back and make phase linking faster again. Yeah, any questions? We're not gonna go super into details of all of the errors because Haresh kind of structured the early talks on many of the errors that Anne has already talked about and that we've done in different days.
We've been accumulating questions in the Q&A.
Yeah, there's
having a
some
look.
stuff for you to look at.
I don't know if I can see the.
Can you see the Q&A? It's
You might have to open it from the menu on your screen or stop sharing.
yeah, if you stop sharing.
Oh, I see. Oh, stop sharing. Q&A. Should I go?
You check the open question.
Open ones?
Yeah.
Do we expect phase linking algorithm to perform better than SBAS at every location or application? That's a loaded question, if I ever heard one. I would say that one interesting thing is that like the way Anne posed it and like the way MintPy has it, that's like the SBAS as it was described in the original paper. The people who do like SBAS TM, I guess it's called now like the PSBAS DINSAR pipeline. If you kind of Google those, you'll see the paper. They do something very similar to phase linking. They have added a step where they form short baseline interferograms, and then they do this nonlinear optimization where they remove phase closure. But they're still calling it SBAS. So I think that has led to a lot of confusion of people trying to learn and then separate what these different methods are doing. Yeah.
But wouldn't your answer be yes?
May I add a comment here for this question? And so there are many different processing methods out there, right? PS, there's DS, there's SBAS, there are phase linking with different algorithms. So my take on this is no matter what method you're using, you're trying to measure the deformation that occurred over that area using the same data set. So really, and all those methods are weighting the noise differently. That's why sometimes one method might work better than the other. So it doesn't hurt to try multiple methods and see how consistent your result is. And if they're all consistent, and likely they're all capturing the same signal. And if there's inconsistencies, my experience is very hard to say there's one winner on all of them. So it's almost like there's inconsistencies. We should go back to see where things are more inconsistent, and then go look into the detail. And that's kind of like sometimes my group even use a simple method called stacking, and it can produce comparable result with the phase linking method. There's no which one is better. I think if we better understand the noise, we should be able to use a different method and get a consistent deformation pattern.
My prejudice, which I am not nearly as invested in this as some of you guys, is that it probably should do better. But whether it's worth it to go through the extra effort is the question.
Yeah, in the end, it's a cost-benefit analysis in some ways. And I think the benefit of it does not always outweigh the extra effort you have to put into the processing.
Indeed. For landslide monitoring, how do you decide how much multi-looking to use? Default is 2.8. That's not my default. I don't agree with that default. I think that's a better office hours question. There's a lot to that as well. I will say that for Opera, you can look on the DISP S1 repo, and there's all the configuration files that will run. And so we didn't do one single configuration. I said it's like, you run it through the thing and it always does the same thing. But like, there's still parameters that affect it, and it was the multi-looking window that was like the biggest knob that made a difference. And expanding the window so that we did more multi-looking in the more vegetated areas and then further north, that was like pretty key to making it not garbage. Like in the paper, there's a Three Sisters volcano and I have like a decently clean signal there. That was about the 9th iteration of that attempt, and the first 8 all had like pretty small multi-lift windows trying to keep fine resolution. And then finally I just expanded it way out, and then it's like, oh, now there's not unwrapping errors everywhere. Okay, now you can see something.
And I can add one thing about multi-looking. So the essential trade-off here is I don't think there is like a single magic number because every case is different. So essentially, when you're doing multi-looking, you're trading off between spatial resolution and the noise level, because it's decorrelation noise. If they're not super severe, you can get rid of those spatially incoherent noise through just a simple multi-looking by quite a bit. But the issue is that if you're having a very fast landslide where your fringe pattern is very dense, when you're multi-looking, you might lose that resolution to resolve those detailed deformation. And in that case, maybe stay with a noisier interferogram that actually has the correct number of fringes is better than a smeared image that lose your signal.
I think Rowan's going to answer that. I guess the short answer of what Gasker's question is going to be is no, it shouldn't smooth out short-lived deformation signals, because just the phase linking only tries to remove decorrelation noise, and so it'll keep the deformation but also atmosphere. So any propagation phase is what the things I showed was going for. Can we change to different backscatters to get phonology? I don't actually know. That is kind of a domain-specific radar question that I don't know, and somebody else would be better answering if you can detect phonology changes.
I think you can definitely use changing backscatter to detect change. We're mostly like looking at the phase measurement, but how do you link it to a specific retrieval? I think you might require some specific radar backscatter modeling in order to do that. I think there might be some cases I see empirical approach to trying to see how much things change with what kind of a surface you have, and then establish some kind of link. But as Scott said, I'm not an expert either on this.
Maybe something with like polarimetry too. So this would be a good question to look at NISAR and the quad pole data.
Yeah, there's a lot of good literature on agriculture mapping with SAR from Canada. Canadian community has put a lot of effort into that. So Googling around for Canada specific papers can help. They use coherence and amplitude change and polarimetry from RadarSat to do a lot of this work.
Confidence of phase linking techniques over faster deforming areas. So I think the only time where really fast deforming areas will be rough is if it's like approaching the kind of the Nyquist limit for how dense the fringes are. Kilauea is probably a better example of that. And from what I've seen, it doesn't do worse. Like the phase linking part of it doesn't do that much worse than just like single interferograms and trying to get ones where you haven't lost the signal from like too dense of fringes. The Central Valley is actually a case where even though it's like meters, the signal is spread over like 50 kilometers or 100 kilometers wide. So there's no dense fringes in the interferograms, and like phase linking will not affect like the fast movingness of that. I tried sweets and it failed. Sounds right. If there should be knobs for processing smaller blocks. Dolphin is there are a lot of configuration options for going up or going down with RAM, and you can basically try and go a little bit slower by loading smaller and smaller blocks and capping the number of mini stacks that you'll see. Yeah, there are ways to. If you ran out of RAM, I run Dolphin all the time on my laptop. Caveats? None. 0. No, I'm actually not sure what kind of caveats you're thinking of. Can phase linking and SBAS be used in the same processing? They are kind of alternatives. I guess actually I can let me do more than that cursory glance at the difference one. This is probably, okay. Yeah, sorry, I have a slide on this. So they're very similar. You start with a stack. For SBAS, you form a network of overdetermined interferograms and you unwrap them. And so they'll mostly agree. If you have no unwrapping errors, the difference of like day 1 to 2, day 2 to 3 minus day 3 to 1, that'll be just like small speckly decorrelation noise differences. And so then your network solve will solve that. And like your noise might look like just Gaussian noise. And that's why you can just do at least square solve. Or the original paper also really emphasized SVD. That's only necessary if you don't have a full network. But often in Sentinel-1, you do a full network. So you're doing least squares. The phase linking alternative looks very similar. And there's just that phase linking step where now, instead of your interferograms that are redundant, having speckly kind of Gaussian type noise, they'll agree because you've removed the misclosure. And now the unwrapping step, you have only unwrapping errors to solve for. And so there's no unwrapping errors. The network is actually completely redundant. And that's why we'll talk about this tomorrow, that there's the default for Dolphin is to do an L1 norm unwrapping because the input is phase linking. And so there's no longer speckly noise plus possible unwrapping errors. You only would have unwrapping errors to solve for. But you can see that they're very similar. And so that's why I guess I would say they're alternatives, but it's really, I mean, I'm at this stage, we're forming short baseline interferograms. So that's why kind of SBAS as a general term is very vague. And this is doing something a lot like SBAS.
Super.
Cool.
I think
And there's 2 notebooks from last year if you wanted to see the synthetic examples, where you kind of make it and then you can do like it has this is not using Dolphin, it's just doing like NumPy to get like the multi-looking and see how you can make phase linking. So this is trying to be like as simple as possible to do, make a coherence matrix, and then you can optimize it to get the eigenvalue. And so you just take SciPy eigauge, and now you can see that this is what phase linking will do as you loop over the rows and columns.
That's, by the way, a fun exercise. These coherence matrices are incredibly enlightening. Kind of learn a lot about your schedules and your environment by looking at these coherence matrices.
Yeah.
And with like Sentinel-1 through OPERA, where we have over North America the deep CSLC stacks, and with NISAR, you should be able to create some coherence matrices fairly easily to just sort of explore your landscape and understand what kind of signals you're seeing, and you see impacts of weather patterns, etc. So there can be interesting information in these coherence matrices themselves.
Last slide, runtime was mentioned. So this is a question where you say there's a lot of 10 years of data. That is a lot. If using ISCE2, that'll be the slow part, I think. Tomorrow when we do Dolphin, there'll be similar runtimes there. You can see, at least, so for the NISAR stack, there's like 8 SLCs, and then you can see it takes a minute to grab your subset, and then phase linking running Dolphin and then unwrapping will take like 5 minutes or so. So it depends on how big 50 by 50. The biggest knob for runtime for Dolphin, and so like for phase linking, is what your output posting is. Because for some libraries or some implementations, they want to output the same resolution as the input. That's like the full. So Haresh's Fringe library first would do that it would output at the SLC posting. And that is pretty slow. There's no way around that I can think of. But what Dolphin has is the ability to output strided outputs, or basically decimated. So instead of, if you want 30 by 30 output and you don't really care about like 5 by 10, then you can skip every third and every 6th pixel from what comes out of compass. And so you get basically an 18 times speed up. And that's why you can process something at like pretty fine resolution. 30 meters is like not bad for a lot of cases. And it'll run much faster than trying to do like an ICE2 for a full frame and then running it and then trying to crop after or something. You can just skip a lot of the steps if you aren't going to need it.
Hey, Scott, I have a question here. So is Dolphin using the same algorithm that is employed in Opera?
Yep.
Yeah.
Yeah, the thing that runs to produce displacement DISP S1 outputs is basically like take in what the Opera data system does, which is the compass, call Dolphin, and then format it as netCDFs. So Dolphin for a while was like 90% of the functionality of the Opera displacement workflow. Opera uses EMI, not EBD.
I think we have finished. We've run out of time
Okay.
for this session, but this was fantastic. The questions could still be answered by enthusiasts in the meantime, but we should take a 5-minute break before we start our voyage into MintPy. The first and maybe simplest of the time series methods. Espace, fantastic. Thanks again, Scott.
Yes, fantastic. Thanks, Scott and Anne. 5-minute break, and then Yunjun will talk about ISPAS.
Welcome back. Next up is Yunjun. Are you ready?
Yes. Let me share my screen. Can you see?
Yes, we see your notebook. Can you show folks what folder that's in, just to make sure?
Yeah, right. If you go here to the ISCE+, we are now in folder 4. We're in session 4.4. We just had some new updates just a few hours ago, so I would recommend you to, as we did before, to delete this folder and update the repository to make sure you grab the new ones. Okay, we got it here. And there is also one more thing is for the compatibility with the NISAR products, we updated MintPy, and only the latest version of MintPy supports this. So please make sure you run the first cell. It does version checking. Make sure you have this ready. If it's not, for example, I think I just tried slightly earlier ones and it's not working. I mean, the version there is not, it's not old, it's not new enough. So you need to go to create a new environment, and by choosing this one instead, and then to build yourself a new environment that has that MintPy, the latest version of MintPy. So that part is required for us to run this notebook successfully. This will just take you like 2 or 3 minutes, I believe.
Can you all test and see where you are with your version? Maybe a thumbs up for folks that have the 1.6.4.
Yeah, it seems that we need to make new environment.
Okay. Should we give you guys a few minutes for that?
Right.
And if you could thumbs up or so once you're ready. See, the first ones are getting there. And so once you've built the environment, make sure that you change the kernel in the notebook to the earthscope underscore InSAR underscore inf, the way it's shown on Yunjun's screen. I've seen a couple of thumbs up, but not too many yet. Are you still working on it?
Yeah, it is still running, like installing.
Okay.
So the people still asking how to recreate the environment. Create that by go to in the home directory, go to the conda environments and create OSL Pixie environments. And in here, you just select them, execute them one by one. And if you execute them one by one, it will allow you to choose here. In here, choose the earthscope InSAR environments and continue to choose here and then continue to run things afterwards. And then you will have all the way to the end. This one, you don't need it. All the way to the end, you will have everything ready.
Yes, you need the Pixie builder. So in the create OSL Pixie, that's the one you need.
This one, right?
But it is in the Conda environments folder. The link
It
is
is in the
correct.
Conda environments
The link
folder.
is correct. The path is correct. You just need to read it.
Yeah. Are most people close? Don't want to delay the progress too long. Some
I
thumbs
think
up.
for me to finish the like in 2 to 3 minutes. Yeah, while I tried to restart the server, I also had issues with the X large. So I started a regular large ones, and it runs up much faster. And I think that is enough for today's notebook afterwards. If you choose a smaller instance.
Okay. Maybe we can slowly get going with the small
Yeah.
baseline app.
Yeah. So if you still have issues, maybe just stick to our section, and then you can try to recreate your environment after the class. So today, in this session, I will do a simple introduction to the time series analysis software called MintPy, and then using the NISAR GAN W products as an input. And today, first, I want to acknowledge the work done by my students, Changyang Hu. He adapted mostly of today's notebook to support NISAR products. And the support in MintPy for NISAR products was done by several people from JPL, including Sarah Miyazaki and Emre Havasli. So MintPy is an open source package for InSAR 10 series. It starts with a stack of unwrapped face, unwrapped interferograms in either geo or radar coordinate, and you can estimate ground displacement 10 series after that. And then you can apply various phase corrections to the 10 series to get a more cleaned version of the displacement 10 series. And the MintPy inputs you can use to feed into MintPy, you need to have the stack of interference processed already with other INSAR processors, such as ISCE. It also supports other INSAR processors, such as Gamma, GMT-SAR, Snap, and Royal Pack. The information, you can find it on the GitHub. The detailed algorithms in MintPy, you can find it in a notebook, in a paper that I wrote with Harash and Fogg a couple of years ago. So in today's session, we will try with the NISAR GunW products because that one is operationally generated by NISAR. But even though it's only there's no redundancy, we only have the nearest neighbor pairs for all the NISAR products, but it can still give us a pretty good view of what is going on the ground without us to really generate the interference ourselves, which is really nice. So today we will try to do that. And before we do all this, let's first run the first cell, which will show us this. So in today's ones, the data structure is relatively simple. We're using the Mexico City data as an example. There's already a couple of months of NISAR data there openly available. And we'll download the NISAR products into the interference directory. We will download an extra DEM, and we will have a MintPy directory with some configuration files, and that's it. Before we do further explanation, let's run the next cells again. These cells will download the NISAR products. So for us to search, you can go to the ASF website, which here I just do it right now. These are just a screenshot with the bounding box that I gave and with the track and friend numbers that I set up to filter out the outputs. We have several NISAR data there, and I believe if we choose products, and then choose the GUNW file here, it'll further show us right now there are about 9 interferograms there available at these sites, and we're downloading not all of them because there's a big jump. You can see the time here. We have the interferogram starting from last year, September, October, and all the way until last month, but then there's a big time gap between June and January. So we're only using the interferograms from January this year and backwards. And here, by running this, we're downloading the NISAR products using the ASF search package. And right now it's downloading them one by one. And you can see your downloaded file here in this folder. You can see we finished 3 of them. We're working towards it. Should be really fast.
So I've had success in the meantime, Yunjin, by going to the Pixie TOML file, which is associated with that Conda environment. So we go to Pixie environments there, and then Earthscope InSAR, and then Pixie TOML.
Yeah.
and then change the version of MintPy from star to 1.6.4, and then rerun the building of the notebook, and it will build it with the right version.
Cool. Cool. Great. Rerun this, right?
Yeah, I think the step before it, yeah.
Okay.
Not that one, but a couple above, yeah. From there on.
Okay. I actually did not change anything, just to rerun this. It seems to work for me as well. Okay, we completed the downloading. I checked actually each one of the Gundam files around 2 gigabytes, so it's relatively large. And let's run the next ones also. This will download the DEM file from the Copernicus DEM using the SAR DEM, the package wrote by Scott. And I believe if somebody is interested to try, you should also be able to download all these using the ARIA tools, which will do the similar thing as what we did here. Okay, let's go forward. This is done. So the workflow of these the main program within the MintPy is called the small baseline app. That is the small baseline approach. Is basically the equivalent. Is basically the classic SFAS approach or the DS approach, as what Scott just showed us. And the application here, the main program here includes several steps, and they are basically categorized into two types. The ones on the blue on the left and the green ones on the right. The blue ones here are doing several operations in the interferograms domain, including the modify the network of the interferograms, select a reference, and do the unwrapping error correction. And then after the network inversion, it will do the S-pass inversion to get us what we call the raw phase time series. And then afterwards, everything including those various phase corrections are done on the time series domain. And then at the end, we can get the displacement time series and try to estimate some time functions such as the linear velocities to it. So some options are optional. They are turned off by default, and then they are these steps with the dashed boundaries. The solid ones are required, and each of the step are initialized, can be configured and initialized with default values in a text file. You can click the link here. It will bring you to let me see. Let me try to reshare it again. Reshare the entire screen. It will bring you to after you click link, it will bring you to the GitHub repository. And here you can see the full configuration file. It's pretty long, and they are grouped by each steps. So but each of them are already defined with a default auto value. And what default means is usually written afterwards, and we have another file that sets all the autos. So the way to use MintPy is to get yourself familiar with this configuration file to know each of the options, what that means, and what it can be changed. And then you can update and then you can just rerun the small baseline app again and again to get the good results, to get the results you are happy with. The process steps for a small baseline app, you can check that with the help message. The small baseline app, the way it runs is very similar to the ISCE TOPS app or the Strip Map app. It has several steps as shown here, and it's doing that one by one. And then you can start with a specific step and stop at once, given that you have already run all the steps beforehand, before it. And these are the few of them. The inputs, basically the load data part steps is to load the stack of interferograms you generated using various InSAR processors into an HDF file. That is what MintPy is using. See, it's the same file, it's a similar file format like the Compass. And the next ones are the network inversion part. This part we already said it, and we will say a few more words afterwards. But before here, we'll just show a quick overview here. This part is not doing anything specific, but it's just generating some quick overview of your InSAR stacks so that you can have a grasp of what your dataset quality looks like. And also there's another one which will show us potentially the distribution of the potential RFM errors from your inferogram stacks. After we do the invert network, which does the S-bus inversion, you will turn your InSAR data into a time series, and in the time series, you can correct various things. These LOD, the first one is called the local oscillation drift. That's a thing specific to MSET. That's the timing machine available on the SAR payload, and that they used to have some local drift or bias in that timing machine on the MSAT satellite, but it's fine for the rest of the satellite as we know it so far. You can correct for the solid Earth tide, the ionosphere, the troposphere, and if you want, you can also remove a linear ramp afterwards and the DEM error or the topographic residual due to the DEM error, and then estimate a velocity afterwards. And after that, you can geocode them into so that it's compatible with in other GIS softwares. So with all these steps, you can change all the parameters you want. And in MintPy, there are two type of configurations. One is the default ones with a fixed file name called this one. It includes all the configurations with default values, and this files is more for the software itself. So this file will be copied over to your working directory and read every time when the small baseline app runs. The second one is what I call the custom configuration. And this one, even though it's optimal, I always recommend it. You can use whatever names you like. Here, I just use simple ones with a TXT format. And this ones is more for the humans, for the users. It can contains selective manually modified configuration parameters. So every time you run the small baseline app with this configuration, the template, the code will copy over the content of this custom template and overwrite the default configuration files so that the program will have your changed value and those others and default values for the remaining options. So here, if we run the next cell, it will write a configuration file for our data sets that we just downloaded. In here, for us to load NISAR data in the processor, we just choose NISAR, and these are the downloaded files that we have with the name patterns. And we also downloaded the DEM. All the rest are just auto or actually no, or we don't need to load each of them anymore because they are all included in this H5 file. The code will know how to do it. For the other configurations, here we set up a special reference in latitude and longitude. And here for the troposphere correction, we are actually using new ones that is just implemented by David Baker. It's called OPERA. I will say more in that part. we're not doing any phase deramping, and so far we're not correcting for the DM error. But we do are correcting the ionosphere as it's already included in NISAR. Okay, so for this part, we just want to emphasize that the input of MintPy is a stack of interferograms that are in that all, which means all the interferograms has to be in the same spatial grid with the same spatial extent and resolution. And if you process multiple pairs of interferograms, in old days with ISCE TOPS app, if you process that multiple times, you're not getting a stack. You are really getting a list of interferograms, and that is not compatible with MintPy. But if you are having a geocoded interferogram stacks or a geocoded list of interferograms, you can read them into a consistent spatial grid, and that is what we're doing today, and that will be working fine. If you're interested if you're interested in other InSAR processors, we have some documentation here that shows us some example data set using ISCE and using ARIA, using others including the ASF Type 3 and GMT-SAR. And for each of them, the expected data structure, we already listed some examples here. And with this data structure, all you need to change is the data file as the input for MintPy, which we are also showed some examples right next to it. So you can try MintPy with other InSAR processors as well, as listed on the left here. So let's go forward. Let's run the first step. We can just run here, which will load the NISAR products into MintPy. And in here, as you can see, it starts to generating the geometries, grabbing that from the NISAR H5 files. Which includes the height, the instance angle of the loss vector, the azimuth angle of the loss vector, and the water masks. Also, if you see earlier here, you can see that's exactly what the code is doing. The code is going to this working directory and copy it over and then read the custom template that we just specified and update the default template based on this custom template. So it's changing the default template from the auto value to the custom values that we just specified. And for all the rest, it's not changing anything else. And one thing is that, let's see if it's already finished. So you can see here a few things with the NISAR is since the GAN-WH5 file has the regular interferograms plus the ionosphere and solid earth type and the troposphere layers all in it. So when we load the NISAR products, we are creating the stack of ionospheric pairs, the stack of tropospheric pairs, and the stack of no, that's it. No solid earth type. That is for the ARIA products with the latest version. So in here, since we have 7 interferograms, we are here in 7, and these are the length and width with interferograms that we have. And after, oh yes, there they are. That's the solid earth. That's the solid earth type stack. Because in here is no redundancy. And within the H5 file, especially the ifgram stack file, it's an H5 file including many metadata and 6 dataset cubes. As explained here, the most important one are the unwrapped phase is a 3D array in the size of the number of interferograms, the length and width. You have the same thing for the spatial coherence and the kinetic components. And we have another 2D array for the dates, which is the reference and the secondary dates for each pair, and the perpendicular baseline for each pair, And the last one here, the drop ifgram, is just a flag matrix to identify which infograms we want to use and which infogram we want to exclude for the various analysis. One core thing is to not using that, whether we want to use specific infograms to do the S-bus inversion. Okay, it finished, and then let's see run the next cell. You can see it creates another a folder called inputs, which has the following files: the if-grant stack, the ionosphere stack, the solid earth, the tropo ones. These are two configuration files. And one thing with MintPy is after the load data, all MintPy need, all the steps afterwards need is just the input files. So if you are doing the processing on your server or on the HPC, after all the massive processing, especially in the InSAR part, after loading into MintPy, you can actually copy over these folders into your local machine and then do everything with that without anything else. And then you should have everything you need to do all the analysis afterwards. So for the H5 file, if you're unfamiliar with it, you can actually check what it is. Is the H5 format is it's very efficient and easy for developers, even though it's not so straightforward as for users. But we provide some scripts to help you with the format. One is called the info.py. It's very similar to the GDAL info. It will show you the structure of the file and what's content inside. Here to show you the basic file information as shown here, and with many attributes or metadata in the root level, such as the number of looks in the Atmos directions, the Atmos pixel size, this UTC time of the center line of your infograms, etc. And with the H5 file HDF datasets that we have, you can run that to any H5 files, not just MintPy created ones, but literally any H5 files that you have. It will show you this type of information. So before we go forward, let's just first plot the network to see what kind of infogram network that we have. These are the NISAR data that we have. This is so we have the data set starting in October, November, December, all the way into January. We have around eight SAR dates which can form 7 consecutive infograms, and these are the coherence history which is pretty high or are above 0.5 and above. These are the coherence matrix, which Scott just showed earlier. In here, one thing that we changed in MintPy this year is we actually changed the X and Y axis into the actual time. And for NISAR, since we have the regular temporal sampling of 12 days, so this looks exactly the same. But if we see the dataset tomorrow, we will see those are nicely those will be changed a little bit. And these are the infogram networks that we have here. The color of so in here, the color of each spot shows represents one SAR image, and each line represents 1 infograms, and the color of the lines representing the average spectral coherence of that single infogram. So you can see ours, even though it shows relatively low or in the red, but they're actually in the upper part or around 0.6 or 0.7. And all these informations are saved in a TXT file called these ones. You can take a look at this here. If we go to the MintPy directory, we have this TXT file here, and you can see these are the data files that we use to generate with these 2 dates. These are the mean spatial coherence and this corresponding temporal baseline and a spatial baseline and the index of this pair around in this whole stack. So you can see the average spatial coherence is relatively pretty high. Okay, and then let's go further. We can generate some quality matrix, quality masks here. One thing is to do the temporal average of all the spatial coherence, so we can get an average spatial coherence. And this is how it looks like for the Mexico City. And we can also generate the water masks. That's shown here. And afterwards, we can generate the connected component mask. And what this does is these are actually the joint. These are actually the common connected components. That means all the white pixels here are having valid connected component among all interferograms. So since so far we're already familiar with it through the class, the valid connect component means basically the snafu. If you're using that as a wrapper to basically snafu think you can get reliable unwrapped face. Unwrapped face with it, and the background, which means is pretty unreliable. So we can see for here we have those background pixels are very little, which is really good news due to the very nice coherence that the L-band NISAR has. In this case, since I will show why do we do that afterwards. In this case, we are generating a mask using the average spatial coherence with a minimum value of 0.2. So we're basically masking out all the pixels with an average spatial coherence less than 0.2. Afterwards, we need to select a reference point before we do the S-bus inversion. And you can see here it should be finished really fast because in here, we're not really changing the data value itself, except just adding a metadata to the H5 file, basically adding the reference point in lat long and XY to the data to the data itself. And when we do the S-bus inversion, the code will read the original interferogram stack, original interferometric unwrapped phase, and apply the spatial referencing on the fly when it does the S-bus inversion. Now let's go next to do the S-bus inversion. In here, so it should finish really fast. The S-bus inversion here, we're just using the classic S-bus as shown in the Bradino et al. Paper in 2002. And besides the time series H5 file, we also generate a temporal coherence. We'll explain right afterwards what it means, and the number of inverted interferograms. Because sometimes for different pixels, especially if we do adaptive pixel-wise multi-looking adaptive pixel-wise masking, for each pixels, the number of interferograms you used for the S-bus inversions can be different. So we saved those numbers here. These are the time series we generated through this step. And then if you run in for the PY, you can see the data structure, which is similar to the ifgram stack, except here we have a time series, which is in 3D cube, and the 8, because we have 8 number of SAR images or SAR acquisitions. And we can plot it to see how it looks like. So these are the NISAR time series, raw phase time series we have. All the fringes here. This first one is the reference in time, so it's all green or all 0. And here we plot these things in a fashion that we rewrapped it into the -5 to 5 centimeters. similar to we wrap it into the minus pi to pi, but the whole thing is actually unwrapped. It's actually unwrapped, and since this step, MintPy changed the data unit from the infograms, which is in a unit of radians, into meters, which is into meters for all the time series files and everything afterwards. And also, since here all the positive values in MintPy indicates the motion towards the satellite along the line of sight directions, and negative values means motions away from satellite. So if it is a substance, then in here then here it will be a negative values in the MintPy time series. So you can see here there's many fringes, which is basically just you will know that it's based mostly the ionosphere. So that's why we will do an ionosphere correction here. And these are what it does is we got the stack of ionospheric pairs downloaded from NISAR GAN files, and they are basically in the same SBAS network as the regular infograms. So in here we will also run a special referencing so that we can apply that to the faces and then apply SBAS inversion to invert the network of infograms, which is here the ionospheric infograms into an ionospheric time series, and then do a subtraction of the ionospheric time series to the regular time series, which is now here. This is done, and you can see this file is the apparent ionospheric phase time series itself. You can see it looks like this. Since here is already referenced in time, and the black square represents the special reference point. And then we can plot the time series after the ionospheric correction afterwards. You can see all those fringes, all those dense fringes are gone. And if you pay attention to the ionospheric phase here, you can see there's some banded artifacts here, as you see as an example here as well. This is an example on the documentation website. These are currently some known artifacts due to the split band algorithms in these preliminary NISAR products. I believe it will be gone afterwards. And if you want to check here, you can go to here to see all these NISAR products documentation put up by SF. And these are the examples that it has. And you can see there are more documentations on how to examine those NISAR products. Go back. The next one is to run the troposphere. In here, we are using, for the troposphere, if we remember what we did here, in troposphere, we specify the OPERA method. What it does is, let me see if I have it. What it does is it's downloading the NISAR, it's downloading the OPERA level 4 tropospheric products from ISF. That is the level 4 products produced by OPERA by using the operationalized high resolution numerical weather forecasting products from ISCE and WF, which is very similar to ERA5, but having a better spatial resolution but worse temporal resolution, and then save that into the single pass tropospheric delay in the zenith direction. And here we can download that and then project that into the radar line of sight direction and use it as an as an alternative to the ERA 5. Let me see. I think we have the documentation of this is here. The documentation is here if you're interested. This I believe this was designed for the Opera displacement products, but then they find that this one is actually can be independent and what is it called, the mission agnostic, so that you can use that actually for any other dataset, InSAR dataset that you liked. And I like this very much because the downloading from SF is so much faster than the regular URL5 downloading from ECNWF website. So you can see for us here, including the downloading and the interpolation, everything finished really fast. So these are the corrections. These are the tropospheric corrected time series. And next ones, we will just show what the Opera tropo products looks like. So it looks like here. So you can see the resolution is pretty high compared with the normal ERA5 products. So after that, after we did all these phase corrections, we can estimate linear velocity for each pixel through the time series. In here, we're just using the classic least square inversion, and this is what it looks like. Note that we only have a time series with a length of less than half a year. So the time series is relatively short, and this is what we have here. It's pretty noisy with a short time spans. But actually, if we subset and focusing on the city areas where the famous big fast substance we have, and then mask it using a threshold. This is a mask from the average spatial coherence with a minimum value of 0.2. So we basically mask out all the pixels with an average coherence less than 0.2, which are these pixels here. And we're focusing on these areas. We can see even though it's less than half a year, we already see the fast subsiding areas from Mexico City really well. The rate here is very high actually. Even this is minus 2.5 to 2.5 centimeters per month. So it's equivalent to around 20 to 30 centimeters per year, really fast. And the features here is consistent with previous research done here. There are several papers relevant. You can check the papers if you want to see the features. And something here, including this part, are the cities. And the sharp boundaries here is because of the hot rocks underground. And here, this part I believe it's a volcano or something. Yeah. So it's pretty amazing that we got a nice infield-gram, a nice velocity with just a short amount of short amount of data here. And with the MintPy SPAS with the velocity estimation, we can also grab the residual from this line of sight from this linear slope feeding, and and save that into velocity standard deviation. That is what we saved here and plotted right here. Even though it's not the official uncertainty, but we can grab some information, have an idea of the dispersion of our linear velocity using these products. And you can see here, this part is where the substance signals that we showed earlier in the Mexico City. And you can see here the linear dispersion. The time series dispersion here is relatively high, which is about over 1 centimeters per month. So this is because the time series here is right now is really short. Okay. Let me just add one more thing let's add one more thing is here. I don't think I think I do just want add one more. This is not the latest version, I think. But let me just add one more and then I will ask a question and then that's it. Here, if we add an extra plot, we can see the temporal coherence and to see how it looks like for this data set. And you can see here for the temporal coherence is basically either all 0 or all 1. And here the question for you is why is that? Why it looks like that? Could you maybe type that in the chat or speak up if you like? Why here the temporal coherence of these NISAR products is all 1. It looks too good. It looks too good to be true, right?
Is it to do with redundancy?
Yes, yes. So that's the thing that I want to point out with the NISAR interferograms. There's no redundancy. We only has the consecutive or the nearest neighbor pairs. There's no redundancy in the S-bus network. So if you want to do an S-bus inversion, the temporal coherence will all be 1, and we cannot really get an idea using temporal coherence, an idea of where the unreliable pixel is, which will show more details in the session tomorrow. So that's why in here, when we plot the final results, we are using a mask from the spatial coherence instead. So that's things that you should be careful. Careful when you interpret the results from this type of analysis. But again, the product is already there, so you can just download it and use it, which is pretty amazing and really save us a lot of computational powers. I will stop right here and let's see if there's some questions. Cheryl asked if we are starting with GSOC or RSOC products. Is there any code where we can generate the split spectrum and atmospheric phase? I actually am not familiar with that. If Scott or maybe other from JPL is still available, they are maybe more suitable to answer it.
Yeah, we left that question up for one of those people to answer, and they have all studiously not answered it. I think they might all be asleep.
So from I'm sure there is code there in ISCE, but maybe it's just right now from my understanding the ISCE code is not as user friendly as the IS2 code yet, but I'm pretty sure the code is there.
Eric's just joining. Maybe we'll ask him.
Yeah.
Eric, since you've just joined, there is a question about how to generate ionosphere corrections for not the sequential pairs. So,
Yes, no, that's a standard part of the sorry, I have my iPad running. The That's a standard part of the InSAR workflow. There's a ICE3 InSAR.py workflow, and one of the options for that is to do the ionospheric estimation from when you're processing from the RSLCs. So that's built into the workflow, and you can actually look at the YAML file that's there in the for the GUNW and see what those options were. We provide it's both embedded inside the GUNW file, as Haresh pointed out yesterday, and it's available as a separate download from ASF. You can open that YAML file and see the options that were used to run the ionospheric estimation from when processing the two RSLCs to a GUNW. There's not a similar workflow yet available for processing from GSLC.
Part of the reason we haven't covered this really at all in the course is that the disk space and the RAM requirements are very large to actually process something from scratch using ICE3. So we took a command decision that we probably couldn't show how to do that with NISAR data.
Yeah, so like this, Mexico City is in the North America, so it's the 40 megahertz bandwidth data, and to run InSAR.py with the 40 megahertz data, it ends up using temporary scratch storage of 500 gigabytes, and that's
double what we give you. Cheryl has a hand up. You can feel free to ask.
Thanks a lot for the very helpful answers. I was just wondering, would it be reasonable if we, for now, just get the GUNW nearest neighbor ones and then add them up accordingly to what we require, like 1, 1, 2 plus 2, 3 to get the 1, 3 ionospheric phase, or would that be very off?
No, that should work. I mean, that's sort of what Yunjin was explaining, where you can just run an SBAS analysis on the ionospheric estimate or the ionospheric stack of the pairs and get the ionosphere for the individual dates, and then recombine those to get the ionosphere for different pairs. I think that's actually what OPERA is planning to do.
Yeah, and that's why we want to show this notebook, that the nearest neighbor pair should still work for many circumstances. But I would be careful if but right now it's still early, right? We are still having many more NISAR products coming up. But I'll be careful to interpret if you're interested on those very small signals, then these kind of non-redundant network you should be really careful with that. But for the very obvious and very fast deformation signal, such as here, I think it's fine.
I see. Thanks a lot. That answers my question.
Sure. And Eileen Young asked, what's the difference between the last two images? One is the velocity, which is shown here, and one is the velocity standard deviation, which is the last one. So one is if you imagine we have a bunch of dots for each pixel, the time series is a bunch of dots, where the x-axis is time, y-axis is displacement, then we just feeding a line here. So this is the slope of that line, and these are the dispersion or the feeding residual of that feeding of the line. And Juan asked, can you re-show the process to fix the kernel? For the kernel, if you go to the home directory in the conda environments in here, what Gareth just shown here in the Pixie environment in here, if you open the Pixie terminal you change the MintPy part from the star to list version number.
You could even put double equals there to force it to be.
And double equal here.
No, in the quotes.
In here. You
Yeah.
mean like this?
Yeah, like that.
Okay. And then you go up to this to open this notebook. And in this notebook, you just do the whole thing from the top to the bottom. And only thing you need to choose is this part. You need to click here and then continue all the way to the end. And after that, if you open your notebook, you will be able to select the kernel, which will show up as this.
And there is a trick to the notebook, the Pixie notebook, in that you don't click through once you've made your selection on the list, you then click on the next code cell. You don't try and run that again, otherwise it will reset.
Yeah, that can be a trap. So if you click on that and you just do
Yep.
Shift Enter, so it would reset. But if you now run the next code cell,
Yeah, if you run the next code cell,
and hopefully the next one, at some point it will tell you which kernel it built.
this is I already
Oh, yeah, here we go. At the very bottom, it tells you that it
done.
built the Earthscope InSAR. And
Right.
if you made a mistake earlier in the selection list, you would get a different kernel here. At the very end, it shows you the name of the kernel. Oh, yeah, at the beginning too. Yeah.
Yeah.
It's a pretty useful notebook once you have used it once or twice and you know how to use it right.
Fabulous. We got through our first MintPy run in less than an hour.
Yeah, and so we have more of this tomorrow. Do you have the agenda up?
I can bring it up. Just give me a second. And at this point, Yunjun, is there anything you want people to do for tomorrow? Because that's another.
It's fine. I think people are testing tomorrow's session is okay. When I may update the notebook a little bit, so you will need to delete your notebook and update it again, but that should be really fast.
Okay, yeah. So the homeworks there's a quiz associated with the exercise that Rowena led us through this morning, Pacific time. It's on Moodle, so please answer that quiz on Moodle. And then the homework for this exercise that we've just done is to estimate the deformation at a location in your data set that you have just processed.
Yep, and then tomorrow we will have more of this. So Yunjun is coming back with a redundant stack of Sentinel-1 images and using MintPy to show off some of the additional capabilities MintPy has. And then Scott Stanovich is going to come back to talk about OPERA data visualized and analyzed in MintPy, and also tell you a bit more about Dolphin, which is the framework he helped build for OPERA that jointly analyzes PS and distributed targets.
Yeah.
And today we still have an office hour. So today again at 5 p.m. Pacific time. If you have questions about homeworks or have other things to discuss, please show up at the office hour.
Yeah, I was wondering if Yunjun wanted us to download the Sentinel-1 stack now, but we don't have to, unless he says.
I think previous year's just finished in like 2 minutes.
All right, we will test our AWS download capabilities live with 150 people trying to download it all at once. We shall
It's
see.
supposed to be scalable.
Yeah, that's what it's. Yeah, it's what the
That's right. NASA sunk all their money into AWS, so we will get your money's worth, taxpayers of America.
Using some of those data centers that are being built everywhere.
That's right. Polluting a river near you.
Well, thank you all for today. I'll see some of you later in the office hour, and we see each other again tomorrow.
Bye, everyone.
Bye, everyone.